हेलो। हेलो।
हाँ अर्पण।
हाँ।
हम्म, अ, ठीक है। यूट्यूब लिंक शेयर कर दिए हैं सबको।
और कौन जितना लोग रजिस्ट्रेशन किया था?
नहीं, जिसको हम लोग नहीं भेज पाए थे उसको, मतलब जिसको अकोमोडेट नहीं कर पाए थे सीट्स में हम लोगों को।
अच्छा।
ठीक है।
हेलो।
हाँ हाय।
हाय।
ऑडिबल है आवाज?
हाँ, मेरा तो मतलब कि हम अपना भी कैमरा ऑन करें देखे, क्योंकि हम तो तैयार नहीं थे वीडियो के लिए।
कोई बात नहीं, आवाज है ना। ठीक है, परफेक्ट हो एकदम। उल्टा आ रहा है इसका।
मेरा
नहीं नहीं, पर मोबाइल से
हाँ,
उल्टा।
अब ठीक है सर।
हाँ ठीक है। ठीक है, मेरा आवाज क्लियर है ना? तो मैं बेसिकली शुरू करूँ, मैंने मैम को बताया सीक्वेंस क्या है। आई विल स्टार्ट by simply saying good morning and welcome to the statistical meta analysis workshop, and then I'll ask ma'am to welcome Professor Guido Knapp, ठीक है, एंड पार्टिसिपेंट्स। एंड उसके बाद मैं इंट्रोड्यूस कर दूंगा सर को, और फिर मैं पार्टिसिपेंट्स के लिए फ्यू पॉइंट्स बोलूंगा क्वेश्चन आंसर के लिए। So I'm going to speak these things. We would request you to not ask questions in the middle of the sessions. This is important to avoid multiple interruptions during the lectures. A question and answer session of 5 to 10 minutes will be there at the end of each session. You can ask questions by raising hand or by messaging in the chat box. In case of any urgent request, you can write message in the chat box. If due to time constraint we are unable to accommodate all questions, we will try to include them after the last session of each day. ठीक है? Sounds good. इतना बोल के बाकी ज्यादा बोलने की जरूरत नहीं है, और शुरू में इंट्रोडक्शन मैंने उनका देख लिया है तो मैं पढ़ दूंगा। ठीक है, तो अब हम लोग वीडियो अभी ऑफ कर लेते हैं एंड यू कैन लेट इन पार्टिसिपेंट्स। ठीक है?
तो सर
ठीक है
अब लोगों को वो एंटर करना शुरू कर दें, एडमिट करना।
हाँ कर दो, अब तो टाइम हो रहा है, शुरू कर दो।
ठीक
ठीक
है,
है सर।
तो हम
मेरी
भी
आवाज
अपना
आ रही है,
लिस्ट
क्लियर
देख
आ
देख
रही
के
है?
वो।
हाँ आ रही है, क्लियर आ रही है तुम्हारी आवाज।
ओके सर। गुड मॉर्निंग मैम।
गुड मॉर्निंग परमीत।
हाँ जी मैम।
गुड
वो
मॉर्निंग।
ज्वाइन नहीं हो पा रहा था ना, तब मैंने तुम्हें कॉल करा था।
अच्छा अच्छा, कोई बात नहीं मैम।
अच्छा,
अच्छा, ये परमित एक ब्लड प्रिंस नाम से कौन है?
सॉरी।
क्या?
एक ब्लड प्रिंस नाम से आया हुआ है वेटिंग रूम में, देखो। स्टूडेंट होगा कोई, हो सकता है। चलो वो देख लेंगे, आगे देखेंगे। स्टार्ट, उनको ऐड करना शुरू कर दो, है ना? ठीक है।
हाफ लगाना भूल गया सर ब्लड प्रिंस के पहले।
ठीक है, तो ऐड करना शुरू करें सर।
हाँ हाँ कर दो, ऐड कर दो, टाइम हो गया तो
ठीक है, तो एक ही बार कर दें क्या एडमिट हॉल?
कर दो, अभी तो सब कम ही लोग हैं, 5-6 लोग हैं।
ठीक है।
Welcome everyone. We are just waiting for our resource person to join. As soon as he joins, we'll start with the session. So please be patient. Thank you. Good morning, everyone. Before we start with the session and till Professor Knapp arrives, I would like to make few announcements for the participants regarding question answer session. So what we had decided that we would basically request you to not ask questions in the middle of the sessions. This will be important to avoid multiple interruptions during the lectures. And we'll have question and answer session of 5 to 10 minutes at the end of each session. And you can ask questions by raising hand or by messaging in the chat box. In case of any urgent request during the lecture, you can write message in the chat box. And if due to time constraint, we are unable to accommodate all questions during the session, during the end of the session, we'll try to include them after the last session of the day. So it will be important to follow this guideline so that we have a very smooth running of sessions. Also, we are streaming our session live for those who could not be accommodated in this workshop because we have limited seats. So we are streaming it live on YouTube. So that link can be used for, and that has been actually sent out to all the participants who were interested but could not be accommodated in this workshop. So we'll also share that in the chat box here so that you can share with your friends who could not be here because of the lack of vacancy. Thank you. Awesome. We have just talked to our resource person, and there is some technical issue in joining, so we are just trying to sort it out. So please be patient for, he should be here in another few minutes. Thank you. Professor Guido Knapp is here now. He was facing some trouble in joining because of some technical issues. Good morning, sir. It is very early in Germany, quite early in Germany.
So good morning. Sorry for the delay. To be honest, I have no idea what happened.
That's all right.
So my Zoom was not really accepted here. So and now finally it works.
Okay, so good morning, everyone, and welcome to the first session of the Statistical Meta-Analysis Workshop. To begin with, I would request Professor Gurpreet Grover, Head of the Department of Statistics, University of Delhi, to welcome the esteemed resource person for the workshop, Professor Guido Knapp, and say a few words to the participants of the workshop. Ma'am, over to you.
Very good morning, Professor Knapp.
Good morning.
All of us welcome you to the Department of Statistics, University of Delhi. We are really thankful to Professor Bimal Sinha for introducing you to us. All of us are really lucky that we are getting share of your knowledge on statistical meta-analysis. Hope you will also enjoy sharing your knowledge with us. Thanks once again to you and Professor Bimal Sinha. Thanks a lot.
Yeah, thank you very much for this kind introduction.
Before starting with the session, I would take a few minutes to introduce Professor Knapp. Dr. Guido Knapp is currently a professor in the Department of Statistics, Technical University of Dortmund, Germany. He has a rich expertise in the areas of statistical meta-analysis, adaptive clinical trials, and mixed linear models. He's a co-author of the book Statistical Meta-Analysis with Applications, published by Wiley in the year 2008. This book is highly regarded in the field of statistical meta-analysis and is a joint work with Professor Joachim Hartung and Professor Bimal Sinha. He has several theoretical and methodological as well as applied research publications in the most reputed international journals. Professor Knapp has been a visiting professor at various prestigious institutions like the Department of Mathematics and Statistics, University of Maryland, USA, Institute of Applied Stochastics and Operations Research, TU Clostel, among others. He received his doctorate and postdoctorate in statistics from the Technical University of Dortmund, formerly known as University of Dortmund. It will be no exaggeration to say that Professor Knapp is one of the contemporary stalwarts of SMA, and we truly feel privileged to get this opportunity to attend his lectures on SMA. Sir, the floor is, we are handing the floor to you now. Up to you.
Yeah, thank you very much for the kind introduction. So you have nearly told everything about me, so it's not necessary that I will say a lot. So maybe just one remark to our Department of Statistics. It's a little bit different, like in India or in the United States. We do not have so many universities with an own Department of Statistics. And Dortmund, my university, we are only the, let's say, the only university in the Germany and Austria with an own department of statistics. So I have prepared a lot of slides for this workshop. So can I share the screen now, or yeah?
Yes, sir, please share your screen.
So but you cannot see my screen light. I do not know what's the problem today. So maybe it's too early in Germany.
So your screen is visible to us, sir. Just enlarge.
But you do not see my slides, right?
No, we cannot see your slides.
So now you can see my. Now you can see my slides.
Yes, it is visible now.
Okay.
Yes.
So.
Better.
Okay, now we have done it. So the original plan was that I give 6 lectures, 3 today and 3 tomorrow for 90 minutes. And the idea is that at the end of each lectures, there will be some kind of a, let's say 10 minutes question and answer session. So we are a little bit late. Let's see how long I will take for the first lecture. So I hope you all have these slides, and I call it now lectures on statistical meta-analysis, and I will also give an emphasis how to use the methods in the R software. So it's kind of a mixture between theory and practice. Just to give an overview, what I will tell you here are first the 5 topics I will, so that the minimum I will cover is you. So today I will give you, after an introduction, first a review of the basic statistical meta-analysis methods. So the idea is especially that in this part you learn about the 2 basic models in meta-analysis after seeing several examples first, and that is the fixed effect and the random effects model in meta-analysis. And will give you the basic statistical methods to analyze such kind of data you will see. And the next step, I will give a little bit more on advanced statistical meta-analysis methods based on the basic methods. And very important thing in meta-analysis is the situation when you have binary data. And I will talk a little bit more on binary data than on other examples here in this workshop. So the first 3 bullets are for, let's say, the analysis, the basic analysis. We will see that meta-analysis usually uses data from the literature. You do not have original data. And of course, when you have a study, you have to publish your result. And of course, not everybody really publishes his or her result. And there is still the risk of what is called the so-called publication bias in meta-analysis. And I will discuss with you several methods how to deal with publication bias. And the last step will be that I've already mentioned the notion of the random effects model. That means that there is some heterogeneity between the studies, and to investigate and explain this heterogeneity, we will use some techniques called meta-regression, and you can also use it for subgroup analysis. Before I really start, I will give you 2 remarks. So I gave a similar, or not a larger workshop for 3 days last year in January in Kerala. And when you go to this website, www.statistic.tu-dortmund Kerala HTML, you will get a lot of data sets in our programs, and also some advanced meta-analysis methods not really covered in this workshop. Maybe tomorrow at the end, I will give a kind of outlook. What will be some advanced meta-analysis methods. And the second thing I will tell you here is there is a website, this prismastatement.org. Prisma stands for Preferred Reporting Items of Systematic Reviews and Meta-Analysis. When you do really a meta-analysis, yeah, so on this website you find a lot of information, and especially a checklist, what you all have to do. And the checklists start from building the hypothesis and finding the data until the analysis and also the interpretation. So, and in this workshop, I will cover only the statistical parts of these checklists. Yeah, but usually meta-analysis is usually a joint work between statisticians and other scientists. So that's a little bit more on the theoretical part, and I will use 2R packages to demonstrate the methods I will talk about. So the first R package is called Meta. It's built in 2007, and most of my examples will be in this R package because it has some advantages for a demonstration when you hear the first time something about meta-analysis. And the second one is Meta4 by Wolfgang Fichtbauer. And this is really the R package with methods implemented that's let's say the biggest or the largest R package for meta-analysis, and you can find everything, nearly what has published for theoretical part of meta-analysis implemented in these R packages. Yeah, and there are also 2 websites, yeah, where you can find some additional information for the 2 packages, and for the R package Meta4, so still the basics, you can find in the reference from 2010 from Wolfgang Fichtbauer in the Journal of Statistical Software. Of course, it's just the basic. It's also a dynamic process all in these R packages. And something about the R package Meta you can find in this book by Schwarzer, Carpenter, and Rücker in 2015. And also there is some information on the second R package called Net Meta, that is for network meta-analysis. And maybe in the last session tomorrow, I'll give you an outlook, especially for the network meta-analysis. So what is meta-analysis? So it's nothing new. So it's based on statistical methods already founded, or not say already developed in the early years of the last century. But the term was coined in 1976 by an educational researcher, Glass, and he said that this meta-analysis, the statistical analysis of a large collection of analysis results from individual studies for the purpose of integrating the findings. In these educational research areas, sometimes you have 50 or 100 studies for, let's say, the same research question. And of course, not all these studies give you the same result, and you have to do some kind of integrating, so the findings from these different studies. And Glass coined this term meta-analysis. Some people like this name. Of course, some people also dislike this name. From, let's say, a theoretical part, let's say the first application usually cited is the, let's say, meta-analysis by Pearson in 1904. where he used 5 independent samples and computed a pooled estimator of correlation between mortality and inoculation, in order to evaluate the efficacy of a vaccine enteric fever. So that's usually the first applied paper you can find, let's say, on meta-analysis. In the physics, there is often cited the paper by Birch in 1932, while he used different experiments at different laboratories to establish reference values for some fundamental constants in physics. And from the theoretical part of their work on meta-analysis in the 1930s, Cochrane, Yates and Cochrane and some others, in the agricultural sciences developed, let's say, the basic statistical models in meta-analysis. When you look in the paper by Cochrane, 1937, you will find a lot of the basics ideas already I will tell you about today. So meta-analysis is now used in a lot of areas of application. I've put here a little bit of a list. I'm working most of the time in this life sciences and clinical trials or epidemiological trials. So while we have the effectiveness of drugs, I also have an example for secondhand smoking. So and in the social sciences, you have reliability and validity studies. For instance, some kind of teacher expectation studies. But you can find a lot of other areas of application like archaeology, astronomy, and so on, where you can apply these work. And a little bit another area where you can also use the techniques I show you today is in interlaboratory trials, where you can use the same methods I will show you today and tomorrow. So usually you can say that meta-analysis consists of 4 parts. And I've already said that's a kind of a collaboration between statisticians and scientists from other areas. And of course, as a statistician, you do not formulate the problem. So the other scientists, they have a question, they have a problem. And that's the first part in this process you have to do. And what you have to do, you can find it in this checklist of the Prisma statement I've shown you. And when you have the problem formulated, you have to think about how you can collect your data. So you do a kind of literature search to find possible studies for the problem you want to tackle. And when you have find, let's say, a lot of literature, you have to review the literature, and then you have to evaluate the literature and to look whether you can find relevant data for your problem in these literature. And when you have the data from the literature, sometimes you start, let's say, with 1,000 papers, and finally you have only 10 where you can find the data from meta-analysis. And when you have the data from meta-analysis, you do the data analysis and the interpretation. So, and the important thing here you have to keep in mind is that I will talk about in this workshop about point 4, the data analysis and interpretation stage. Also, I've already said that the results are usually from published studies, so that you do not have the original data. When you're in the lucky situation that you have original data, you can simply combine the data in mixed linear models. So that's the usual technique you can use, and you do not have to use other methods than the mixed linear effects models. There is this Cochrane, so it's important that there is an E at the end, because in meta-analysis also another guy named Cochrane plays a role. There is Cochrane, an epidemiologist, and I don't know whether you, maybe also in India you will have a Cochrane, let's say, group, and it's based in England and Great Britain, and then have a handbook, and they give some kind of motivation why you have to do statistical meta-analysis. And here are 4 points that you have to keep in mind why we do the meta-analysis. We have the results from several published studies, and maybe the studies are not so large. And you can do the meta-analysis then to increase power. And of course, what you also do when you increase the power and you have more data, yeah, you can improve your precision. Also, and that's also important thing number 3 here, you can answer question not really posed by the individual studies. That simply means when you have an individual study, you planned this study for, let's say, a certain question, and you have some, let's say, other results presented in these individual study. You also can start using these results to do a meta-analysis. And also that the last point here is to settle controversies or generate new hypotheses. Yeah, so the last thing is also important, that sometimes when you do the data analysis and the interpretation stage, it could be your result. Maybe you need more data. Maybe you can change your hypothesis, yeah, or simply, let's say, what is down here, generate new hypothesis. And for the point 3 here, the additional part, I want to, or what I say additionally is, since the results are usually from published study, meta-analysis is always a retrospective analysis. Yeah, so you cannot plan what to do before the studies. You simply have to use the results from the published studies. Yeah, and that's the reason also why you can answer questions not posed by the individual studies. So now I'll give you several examples to give you an idea what we will do in meta-analysis. And these examples cover a little bit the different areas and the different models we can use in meta-analysis. So the first example, Professor Bimal Sinha was already mentioned here in the introduction. So that is one of his favorite examples here. That is the 4 experiments we have here about the percentage of albumin in plasma protein in human subjects. So these percentage of albumin in plasma protein, so that's a kind of constant. It's around 60. And before you find these results, that is around 60, you do different experiments, measure the percentage of albumin, and then you try to combine the results to get a good estimate of the true percentage of albumin. So you can say that these, like in physics, this percentage more or less is a constant. So what we can have here is we have 4 experiments, A, B, C, and D, with different sample sizes, and we observe the mean. Yeah, and also we have a variance, the sample variance. And usually when you look at this data, and you have 4 experiments, 4 different groups, you would say you can simply do a one-way analysis of variance. So that's correct. But when you look here at the variances, you cannot really assume that you have homoscedastic variances in the 4 experiments, and you have to consider heteroscedastic error variances. Yeah, but so that's usually what you can do here is what is known in mathematical statistics. That's a common mean problem. And let's say the common mean problem is a special case of the meta-analysis. So the second example here is from, let's say, more or less the social sciences. That is that we have correlation coefficient for the teacher indirectness and student achievement. We have here 7 studies. We have the number of teachers, yeah, and there is a kind of correlation coefficient given, in all the studies. Yeah, and the question here is, what is now really the correlation? And you see here that that is not really a constant result, in contrast, let's say, to the example here where all the results are around 60. Yeah, so we have here a correlation nearly nothing, up to a correlation from around 0.5. And the idea now is to combine the results from the different studies to get, let's say, an overall result for the correlation between the teacher indirectness and the student achievement. Yeah. So, and the information we have here from the study's correlation coefficient and number of teachers is sufficient to do the meta-analysis. You will see later on why this is sufficient. Another example, a little bit goes in the direction of the binary data. We have here the number of patients and mortality rates from all causes of for 6 trials comparing the use of aspirin and placebo in patients following a heart attack. And that's important now that you recognize that this is already a special data situation. We have here the aspirin, we have here the placebo group, we have here the number of patients, and we have here the mortality rate. And the same here. And we have 6 studies with different mortality rates in the studies. And question may be first, what is the mortality rate in aspirin group? What is the mortality in the placebo group? And on the other hand, you want to know what is the difference between aspirin and placebo. And maybe you can use the difference of the mortality rates as a, let's say, the parameter of interest. And this parameter of interest we usually call effect size in meta-analysis. And what's important here is that you have a kind of a flexibility. I've already said that you can use the difference of the mortality rates as an effect size, but you can also use the ratio. It's another, so it goes in the direction of a relative risk. And the important thing you have to keep in mind here, given that maybe you know the number of patients and you know the mortality rate, so you can reconstruct the 2x2 tables in each of the studies. Based on the mortality rate here, you can calculate how many patients died in the study UK1 and how many patients did not die. So it's possible that you can reconstruct, given this data, the individual 2x2 studies in the different studies. So the 2x2 tables in the different studies. And we will see in this, let's say, lecture on meta-analysis of binary data that you have several possibilities to analyze these type of data. Another example here is the secondhand smoking, whether it's causes lung cancer or not. And so that's now a little bit a different situation compared to the example before. We have here in the 10 studies, no, sorry, in the 19 studies, yeah, let's say the number of cases, and we have estimated relative risk. Yeah, originally these are odds ratio, but when you, let's say, work a little bit in the area of epidemiology, sometimes when the risk is relatively low, you know that you can use the odds ratio as a good estimate of the relative risk. But the important thing here is that we have the relative risk here with confidence intervals. So that's the information we have here. And these data situation is also sufficient for doing meta-analysis. Yeah, so what we in general need for doing meta-analysis is that we have to consider an estimate for the parameter of interest for the effect size. And then we need some information about the precision of the estimate. And this could be the variance and the sample sizes. That could be the information here on the mortality rate and the number of patients, which is also sufficient to calculate, let's say, standard errors of the estimates of effect size you have. Yeah, and also the confidence intervals. Yeah, you can extract the information on the standard error. Yeah, I will show you an example in several minutes how to compute the standard error from the estimated or based on the confidence interval. Yeah, so but this is also a data situation that you can have in meta-analysis, but in contrast also to this example here, where we have maybe the choice between the difference and the ratios of the mortality rate, here we simply have to use the relative risk. Yeah, so we do not have any chance to change, let's say, the parameter of interest, the effect size. When we only have the estimated effect size, we have to use this effect size. And also what you should see here a little bit is, let's look at this example here. So the estimate here is not in the middle of the confidence interval. Yeah, so for the relative risk, the confidence interval is not centered about the estimate of the relative risk. When you go on the logarithmic scale, you will see that the confidence interval is centered about the logarithm of this estimate here. And that simply should give you an idea that maybe sometimes it's better to do a meta-analysis not on the original scale here on the relative risk scale, but sometimes it's better to do it first on the log scale of these effect sizes and back transform the result to the original scale. But we will discuss this also later on. And I think that's the last example here. So these are 13 trials on the prevention of tuberculosis using certain vaccination. We have two groups here, the vaccinated and the non-vaccinated group. And you look whether they have a disease or no disease. And these are in 13 trials, and you see that the sample size, when you look at the sum of these disease and no disease numbers, are quite different. And some studies are relatively small. Some studies are rather large. And I have already learned that trial number 8 with these larger numbers here was a study in India. And of course, you can do the meta-analysis with the question whether this vaccination is successful or not. But we will see that there is a lot of, let's say, heterogeneity between these studies. and you can try to explain these heterogeneity. And what you need in meta-analysis is that you need some kind of covariates on the study-specific level. And here's a possible covariate which will play an important role in the meta-regression approach. Here is the latitude, simply to say where the study was, and everything is on the northern hemisphere. So this is a situation after combining the results, maybe, and you will see that there is a lot of heterogeneity in this meta regression. You can try to explain these heterogeneity. And the important thing is that the covariate has a meaning for this problem. And we will see that for the vaccination, the latitude has a good meaning for the interpretation. So next step is simply the data. We have seen several examples. And I've told you that based on these data situations, we can do the meta-analysis. And usually what you can discuss first is whether you have raw data that's still very rare, or summary statistics. And I will only talk about the second part here when we have only summary statistics. As I've already mentioned, when you have raw data, you can do mixed linear effects models for combining the different results. Let's say in former times, sometimes you only had the situation, that only p-values were reported in the studies. And when you only have, that's to say, the p-value is less than 0.05, of course, you cannot do anything with it. You do have to know the exact p-value. And then there are some methods for combining p-values, so to get a kind of conclusion. I will not discuss the combination of p-values here in the lectures with respect to a final conclusion. Tomorrow we will see in the part of the publication bias that you can use these combination methods for the p-values for judging a little bit whether publication bias is present or not. The usual situation you have is that you have an effect size plus the standard error. And this is the data required for meta-analysis. So it simply means you have to have an estimate of your parameter of interest, and you have to have an information about the precision of these estimator, whether it's the standard error or the variance of the estimate. It doesn't matter. It's sufficient that you have an effect size estimate plus a confidence interval. And I will show you, I think it's on the next slide, how you can compute the standard error from a confidence interval. It's also sufficient when you have an effect size estimate plus an explicit p-value. So then is also you have sometimes the chance to recover what was a standard error behind the computation of the p-value. But of course, you also, then again, you need the exact p-value, not the information maybe that the p-value is less than 0.01. And there are some situations where it's also sufficient, like in the correlation coefficient example, where you have the effect size estimate plus the sample size. So, and here are two examples from the one example with this correlation coefficient. It's sufficient that you have your sample size n equals to 10. to do the meta-analysis, because there are some, when you calculate the standard error, the standard error only depends on also on the correlation coefficient and the sample size. And this is the, let's say, standard data situation you need in meta-analysis, that you have an estimate. I will explain you today what is D, and the standard error of D. And when you have these data from all the studies, you can do meta-analysis. So in the example of the secondhand smoking, we had the relative risk and the confidence interval. And the questions is, so that's kind of a little bit of data, let's say, pre-computation, or what you have to do before the meta-analysis, is how can we now extract the standard error of this estimate. And as I've already said, this note that this interval is not centered about these estimate. When we will talk about relative risk or odds ratios, the meta-analysis is done on the logarithmic scale. And also what you first have to do then is that you have to log transform the estimate and the bounds of the confidence intervals. And when then you look at these transformed bounds of the confidence interval and the estimate, you will see that this estimate then is in the center of this transformed confidence interval. And usually what is known as the vault confidence interval is that you have the estimate plus minus the standard error times the critical value from the standard normal distribution. So, and when we are on the log scale, we think that these now was the confidence interval which has been calculated first. And then based on these results with the exponential function, it was back transformed to the original scale, because you want to do the interpretation on the original scale. But for doing the meta-analysis here, it's better to first transform the results to the logarithmic scale. And when you assume that there is the qualt confidence intervals that we have here, the critical from the standard normal distribution, you can first calculate the length of this interval. So that is 2 times the standard error times the critical value from the standard normal distribution. So, and then simply when you know that this is simply the length, let's say here length CI, you can find the standard error of the log relative risk by dividing the length of the confidence interval by 2 times the critical value of the standard normal distribution. So starting from this part here at the top, going here to the bottom of the page, when you have the log relative risk, you can compute the standard error of the log relative risk, and then you have the data situation which is necessary for meta-analysis. And then you do the meta-analysis on the logarithmic scale and then back transform it to the original scale, the relative risk scale. Okay, so these are the first part in this first lecture. So you have seen different examples and you have seen different data situation. What you have to keep in mind is for do the meta-analysis, we need an estimate of a parameter or effect size of interest, and we need an information about the precision of this estimate. Like the standard error or the variance. And when we do these meta-analysis just based on these data, effect size estimate plus standard error, there are two models you can use. Yeah, so and what I will describe here now as the generic meta-analysis methods or models. And you can apply the two models I will discuss now to all effect size estimates and standard errors, whether you have a mean from a normal distribution, a difference of normal means, yeah, whether you have a relative risk or odds ratio, a correlation coefficient, maybe a hazard ratio from survival data, everything fits here in these two models. So a little bit notation here. So the important part first is that we have K independent studies. So the important thing is that you should not include studies in meta-analysis where some kind of overlap of the results. So sometimes in epidemiology, yeah, you have a long follow-up time, and maybe there is a first paper after 5 years follow-up, and then after 10 years follow-up. And of course, the results from 10 years follow-up, let's say, correlated to the results of the 5 years follow-up. And then you have to decide which of the two publications you will include in your meta-analysis. Yeah, it does not make sense because the results are not independent to include both of the studies. So that's important that you have independent studies. And from the notation here is that with theta I will always use the true effect size in the ith study. And with the theta I had the estimated effect size. And based on or using these estimated effect size, there is a true variance. You do not know. The only thing you have to know is that you have an estimate of these true variance of your estimator. And usually, so I only use here in some situations the notation that the variance depends on or is the variance of this estimator here. I will then switch to this notation here, sigma I square hat. But this notation is sometimes a little bit misleading because that's the usual notation you use, let's say, for an error variance on estimate of the error variance in linear models. And the sigma I square is then the population parameter, and the sigma I square hat is an estimate of this population parameter. In meta-analysis, you have to keep in mind that the sigma I square hat is always an estimate of the variance of an estimator. That's important. So, and the starting model simply is that we say that our estimate from the ith study is at least approximately normally distributed with a true theta I as the effect size and the variance. And of course, we do not know the variance. We have to have to know at least, sorry, estimate of this variance. Yeah, so that theta I had and this sigma square of theta I had, these are the data situation. So what is the justification for the normal distribution? Maybe you can say it's a central limit theorem, yeah, or often it's a maximum likelihood estimator, and you know maybe that the maximum likelihood estimator is asymptotically normally distributed, yeah, so that these normal distribution assumption can be justified. So, and then the methods we will simply use, yeah, are all borrowed from the mixed effects model theory for the statistical analysis. Most of the time we simply have the one-way analysis of variance with heteroscedastic error variances in mind, where we do not have the individual data, but simply, let's say, the mean in each group and the variance of the mean in each group. So that's the idea behind the analysis I will show you now. So first of all, we have the fixed effect model. And there is the so-called homogeneity assumption. That means that the true effect sizes in all the studies are identical. So that the theta is a common effect size. And recall in the first example with the percentage of this albumin and plasma protein in human subjects, you can say that this homogeneity assumption is fulfilled. Also, when you want to determine physical constants or so on. So there are some, let's say, problems where you can really do this assumption and can justify this homogeneity assumption. Yeah, and also we will also see that you can test for this homogeneity assumption. And then simply the fixed effect model of meta-analysis is given here in these simple form. And also I switched a little bit here the notation, but that's the notation you usually find in the literature now for meta-analysis, that sigma I square hat, the estimate of the parameter, is normally distributed with the true or common effect size as the mean. Yeah, and then the sigma I square hat as the variance. So that's a notation. Sometimes to be honest, I do not like this notation, but you can find it now in the literature because you have here now an estimate as a parameter. And the idea of, so the justification is that in the following now we treat these estimated variance as a true parameter. Yeah, so I prefer a little bit the interpretation to say that we do the analysis conditional on the observed variance. Yeah, but that you have to accept now. Yeah, so that simply these here is that the estimated variance of the estimator is treated as a fixed constant. Yeah, so and when you do here also they have this conditional, so conditional on this observed. When you do maximum likelihood or simply best linear unbiased estimator, you will end up with this estimator here. Yeah, so that's a weighted average, and the weights VI here are nothing else than the inverse of the variances. Yeah, so this is the first estimator we have here. So that's the estimator in the fixed effect model. Yeah, when you calculate the variance, of course, again, under the assumption that the sigma I square hat is fixed, then you will end up that the variance is 1 over the sum of the weights. So, and for the wild type confidence interval, so that in all situations, an approximate 1 minus alpha confidence interval you will get for this common mean. Yeah, when you center your interval around the fixed effect estimator plus minus the standard error of this estimator times the critical value of the standard normal distribution. So this is the fixed effect model. Yeah, under the homogeneity assumption that in all the studies, the true effect sizes are the same, that we have a common effect size. Yeah, so, and as I have already told you, in some situations you can justify the homogeneity assumption. In some situation, you will, let's say, check the homogeneity assumption and you can test it. And now here is now the Cochrane without an E. So usually it's done by Cochrane's Q. So that is given in this formula here, that you look at the difference between your study specific estimate and the fixed effect estimator, do the square of this difference and weight it by the inverse of the variance and then sum it up. And what you can show is that these QC is approximately chi-square distributed with k-1 degrees of freedom, and you will reject the null hypothesis of homogeneity if these Cochrane's Q is too large, larger than the upper critical value, or 1 minus alpha quantile of a chi-square distribution of k-1 degrees of freedom. So and sometimes you want to check really, and what you want to have is the null hypothesis. So and with the playing of the type 2 and type 1 error, sometimes you find in the meta-analysis literature that I do not know how it is in India. So in Germany, we often use 5% as a significance level. So in this homogeneity test problem, so sometimes we use 10 or 20% for the type 1 error. So these are not really unusual. So and what would you do when we have no homogeneity? And there are different approaches how to motivate the so-called random effects model. And I like this part here, this hierarchical model. And you can see say that is a normal hierarchical model. And the observational model is given in this form here, that we have here the different expected values in the different studies. And then we have a kind of a structural model that you say that the effective or the true effect sizes in the different studies also come from a normal distribution with a parameter theta and a variance tau square. And when you do the marginal model, so given that, so theta I had given the parameters here, you end up with this result that marginally the theta I had is normally distributed with effect size theta and the sum of these two variances. So this tau square is called the heterogeneity parameter, or stands for the between study variability. And of course, the sigma square is again the within study variability, the variance of the estimator here. So when in contrast to the fixed effect model where theta is the common mean, here now we call the theta an average effect size. So in the literature also you find sometimes the notion of the overall effect size for the theta, but now in the last years it has changed a little bit so that we will talk about the average effect size. So and given now this model here, that is the so-called random effects model. So that we have our estimate coming from a normal distribution with parameter theta, and as the variance, we have the sum of these two. So what we have to do here is now, beside estimating theta, we also have to estimate tau square. And starting first with estimating tau square, assuming that tau square, so with estimating theta, assuming that tau square is known, we end up with a similar weighted average like in the fixed effect model. So the only difference are the weights here. Now it's 1 over the sum of these two variance components. So and to use these estimator, of course, you have to plug in here an estimate of tau square. Yeah, and one of several estimators available for estimating tau square is here the so-called Desimonier estimator, which is based on these Cochrane's Q. And what you simply do is that you use Cochrane's Q with these weights VI, so only 1/sigma I square. Yeah, calculate the expected value of these Q under the random effects model, and then simply do the methods of moments estimator procedure. Yeah, so, and what you see here is in the numerator, we have here difference. So, and of course, this difference can be negative, though this tau square should be non-negative. Yeah, so usually what we use here is a truncated version that we use the maximum of 0 and the estimator calculated here for the meta-analysis. So, and there are some measurements for looking at the amount of heterogeneity. So this is I square. There are some benchmarks of this I square, but I do not want to talk about this I square because it's a little bit misleading because of the interpretation, and there is a reference here given that when you're interested in, you can look at that this I square is not an absolute measure of heterogeneity, though in the literature it's often interpreted as an absolute measure. So that's not true. Yeah, so starting here now, when you plug in the estimator, here we have the estimated weights, and you can calculate again an estimate of the variance. Yeah, and you can build confidence interval here in the standard form that you have your estimate in the random effects model plus minus the standard error times the quantile of the standard normal distribution. So these are the two basic models what we have here in meta-analysis. So just to give a short summary again. So this is the fixed effect model. We assume that each of the estimates have the same mean, the common effect size. We need the information about the variability of the estimator within the study and treat these variants as fixed and known. Yeah, whereas in the random effects model, yeah, we have as an estimate as a true parameter now this average effect size. Yeah, again, the estimate of our estimate from the study and treat these as fixed and known. And additionally, we have the heterogeneity parameter tau square. And these is now in the random effects model, the second estimator we have to estimate. So these are the two basic models you have to know in meta-analysis. And I will always switch, let's say, between the random effects and the fixed effects model. And what you have to keep in mind simply is if this tau square is equal to 0, then the random effects model, let's say, collapse to the fixed effect model. So this is, let's say, the first theoretical part, and maybe, of course, we start a little bit late, but now it's, I think, the end, usually end of the first lecture, and maybe you have some questions, remarks, so that after, let's say, the lunch break, I can continue with some examples.
Thank you, sir. We can take, I think, 1 or 2 questions at max, and if there are more questions, we can take at the after the last session, maybe.
Yep.
So please, if you have anyone has any question, either raise your hand or you can type in the message box. Okay. In the meantime, sir, I have one simple question. It was so suppose in a study we have credible intervals based on posterior estimates instead of confidence interval. So can they also be used in meta-analysis? Can that information?
I mean, I think it was credibility intervals, right? So that's a kind of
Yes.
the base. Yeah. So that's, let's say, the Bayesian approach.
Okay.
Yeah. So, but of course, yeah. So that's a good question. So, usually what I have to, maybe I have to ask my expert colleague on the Bayesian part. To be honest, I have never seen the combination of, let's say, the posterior mean and the credibility interval from the Bayesian analysis. So there is a lot of work now for the Bayesian part, because when you assume this normal hierarchical model, yeah, that simply looks that you have to use a Bayesian approach with a priori or a prior distribution for theta and tau square. But really, of course, I think simply you can use it because you have the information about an estimate, yeah, and maybe also you have an information about the precision. Yeah, but simply, to be honest, I have never seen in a meta-analysis because maybe the reason is that I work a lot on, let's say, in the area of the clinical trials. And of course, there is not so many, let's say, Bayesian approaches in clinical trials. But I think it should be possible. So I have to keep it in mind, your question. Very good.
Thank you, sir. So there is one more question from a participant. The question is, how much is sufficient studies for meta-analysis? Is how many studies should be included? Is it?
A very good question. Usually that's the standard question. So the answer simply is to do all the computation. K equals 2. You need 2 studies as a minimum. And sometimes there are some situations where you only have these 2 or 3 studies. Of course, when you look at the results here, going to the confidence interval, yeah, so these are approximate confidence intervals. And of course, the larger the number of studies, the better is the approximation to the normal distribution. And but for calculating everything I will show you, you only need the results of 2 studies. And there are some examples, especially in the clinical trials, where you have to combine the results only from 2 or 3 studies. So in some areas, like the educational areas where Glass coined this notion meta-analysis, sometimes you have 50, 100 studies, so then it doesn't matter. Yeah, but the minimum number really you need for meta-analysis is just 2.
Okay, thank you very much, sir.
Yep.
So there are no more questions. I think we can break for now, take break for now, and meet again at 1:30 IST.
Yep.
So. Thank you very much, sir, and all the participants. Will meet again. Please try to the participants. Please try to join back at least 5 minutes before the start of the session.
Yeah. So, and I also will give my best to join you in time. So I hope I do not have any problems now to join the meeting. So, okay. See you. Thank you.
See you. Uh, Welcome back, Professor Knapp, and I think so. Whenever you are ready, please you can start with your lecture.
No, it's okay. Thank you. So, and can okay. So, welcome back. Now the second lecture for today. And I first will give you an example and a little bit show you the first example how to use R for analyzing these small data set. So this is an example of 3, 6, 8 studies comparing a treatment called amlodipine against placebo. And the information we have is in each group, the sample sizes, the sample mean, and the sample variances. And we are interested in the difference now between amlodipine and placebo with respect to the means. So the effect size simply is here, I've called it here delta, so that difference between the mean in experimental group minus the mean in the control group. Of course, it can easily be estimated by the sample difference of the sample means. These effect size and the variance given independent or independent groups is simply the sum of sample variance divided by the sample size. And when you do these, given the data set, these kind of calculation, you can do the meta-analysis. So that is, we have here the values of DI, the difference of the sample means, and the estimate of the variance of the difference of the sample means. And you can simply perform, when you get this data, the meta-analysis using the function meta-again for generic meta-analysis in the R package meter in the following form, that you have the function meta-gene. The first argument T is the estimate of the effect size. And now it's the important thing is that the second argument should be the vector of the standard errors, not of the variances. You have to take the square root of this. Yeah, and with SM as a summary measure, here is your, I haven't used any title or heading. Yeah, here you can also use it only in this meta-again function for a kind of a heading. So I've included the original R code also here in my slides now. So these are the data sets. Here we have the calculation of the difference of the means. Yeah, and we have here the calculation of the variance of the difference of the means. Yeah, so and oops. Yeah, so the important thing here is in the last line here on this page, that given these DI and the variance of the DIs, we can use the meta-gen function to do the meta-analysis. So the first argument here is the vector of this difference of the sample means, and the second is the standard error that we have to use the square root of the variance of the DIs here. So I simply want to have a title or a heading here, MD for the mean difference. So, and then you have two possibilities, just to print the R object meter one or simply give a summary of meter one. Normally, we just look at the summary of meter one on the next slide. I have this print so that I get all information of this object meter one. Yeah, and finally, I will discuss with you what is the forest plot. So, and this is the result you will get when you use print this object. And there are some interesting things we have to or can discuss here. So first of all, so that the main difference between print and summary is that with the print function, you also get this information here. So for the summary, it's only here, the second half of the page or of the slide. You get here the individual estimate. So the difference of the normal means you have calculated. Yeah, and you get here the 95% confidence intervals in the different studies. Yeah, so and looking whether 0 is in the confidence interval or not, you see that you have a significant effect in study 1 and 2, non-significant effect in 3 and 4, a significant effect again in 5, non-significant in 6, significant in 7, and non-significant in 8. So these are the basic results now calculated given the information of the difference of means and the standard error. And of course, here we also always have the wild type confidence intervals with respect to or using the critical value of the standard normal distribution. Yeah, because we did not include any information about the sample sizes. And there is still a discussion whether you should present here the T intervals, but I think it's not yet implemented. The last two columns here are are very, very nice and important. Here you get the percentage of each of the studies with respect to their weights in the fixed and in the random effects model. So here in this column here, we have the fixed weights of the fixed effects model. So simply meaning that there's 1 over VI divided by the sum of 1 over VI. Yeah, and you see that the first study contributes 21% to the overall estimate, the second 11, and so on. And in the last column, you get the corresponding weights for the random effects model. And what you should see here is the following, that larger studies with a large weight in the fixed effect analysis, a little bit weighted downwards, and studies with a low weight in the fixed effect model, so a little bit upwards weighted. And that's always the situation when you compare the fixed and the random effects model. Yeah, so maybe I go back to the weights given here. So these are the weights in the random effects model. Yeah, and now we get the WI divided by the sum of the WIs in this last column. Yeah, and the larger now the estimate here of a tau square, the more equal are these weights. And when, from a mathematical point of view, when tau square goes to infinity, all the weights are identical, and so that the the random effects estimator then is simply the sample mean of the study specific estimates. So the larger the heterogeneity parameter, the more equal the weights. And that you can see here with this weights. So that is the effect you always observe from the fixed effect to the random effects. And that's also some part, let's say some people criticize this kind of use of the random effects model because of this fact that the larger the heterogeneity, the more equal are the weights. Yeah, because simple people say that if I have a very precise study, also this study should go with these high precision into my meta-analysis. Yeah, but simply that is the fact here, what you can see that the effects in the random effects model are more equal than in the fixed effects model because of this heterogeneity parameter. Yeah, so, and I like the presentation here in this R package because it's the only R package I know in meta-analysis where both results are reported. The result for the fixed effect model and the result for the random effects model. And meta-analysis is always retrospective. I have already said in the first lecture. Yeah. And what you can always do is a kind of sensitivity analysis that you simply look at the results of both models, whether they coincide or not. Yeah, and this is a kind of an extreme example here. It doesn't really matter whether you use the result of a fixed effect model or the random effects model. Yeah, so the estimates of the mean difference, whether you assume it here as a common mean difference or as an average mean difference, are relatively close together. And the effect of the heterogeneity in the random effects model is that we have a larger uncertainty in the random effects model so that the confidence interval is wide. Yeah, so, and then you can calculate also the set values for testing. Yeah, I've just always considered here the confidence intervals in my slides so that the set is nothing else than the estimate divided by the standard error of the estimate, and then you get the p-values here. Yeah, a very small p-values in both situations. Yeah, so that you can say that this treatment amlodipine is significantly better than placebo in this question we have. Here then we get the information about quantifying the heterogeneity. The standard here, what we see here is the decimally layered estimator for tau square. I have already introduced these estimator on one slide. The rest here we simply ignore, h and I square. And the test of heterogeneity, I also could say homogeneity, this Q is Cochrane's Q. I've already introduced. And the p-value here is 9%. Yeah, so it's a little bit difficult based on, let's say, the p-value here, whether now you use the 10% or not. Cutoff value or significance level to choose between the fixed effect and the random effects or the random effects model. But in this example, yeah, so it does not really matter which of the models you really use. The standard in at least the clinical trials or biometry is that you always use the random effects model because of the wider confidence interval. It's always a little bit more conservative than the fixed effect result. And we will also discuss a little bit later on that the results here, yeah, so it's not really based on 95% confidence intervals, it's just approximate 95% confidence intervals, and it could be that the actual significance level is much smaller for the confidence interval than the nominal level. Yeah, and here you get some additional information. So what I've discussed with you is the so-called inverse variance method, yeah, because of the weights, and the decimally layered estimator is here the standard estimator for the heterogeneity parameter tau square. Yeah, so these are the first result from an R package. Yeah, so there is a graphical representation for the results, and that is a so-called forest plot. So this is the standard forest plot without any changes you will get in this meta package. And let's look at what's given here. So we have all the information from the print of the object here given. So the studies, the effect size estimates, and also now the standard errors. Yeah. So here again, we have the effect size estimator now plus the confidence intervals and also the weights in the fixed in the random effects model. And we have here the individual confidence intervals given for the 8 studies. Yeah, of course, in the middle is always the point estimate, and the size of these squares is proportional to the precision of the studies. So that simply means the larger this square is, the more precise is the study. Yeah, so that you get, let's say, an visual a view, let's say, on this data set that maybe the study 7 has a very, very low weight. What you also see here, you can also see it with respect of the size of these square. Yeah, and then we have in kind of, let's say, diamonds, the result here of the fixed effect model and the random effects model. Yeah, and we see that the conclusion here will be the same whether we use the fixed effect model or the random effects model. Yeah, and some information here also still given on the heterogeneity, the tau square, and the p-value from Cochrane's test. Yeah, so and usually you have to report the results given here in the summary, yeah, and alternatively, you have the possibility to show these graphical display, the so-called forest plot for your results. So in the random effects model, there's not only the decimally layered estimator. There are a lot of estimates for the heterogeneity parameter tau square proposed in the literature, and it's not really clear which one one has to use. So beside the decimally layered estimator, we have the polymondal estimator, maximum or restricted maximum likelihood estimator. Yeah, Hunter-Schmidt, Siddick-Jonkman, Hedges, and the empirical Bayes estimator. So I think on the next slide, I have just the formula for a polar estimator. So the other formulas are not really of interest here. So there's just one thing you have to keep in mind, the heterogeneity parameter tau square. So the parameter space is a real positive line, including 0. And all estimates here may give you an estimate of 0, except the Sittig-Jonkman estimate. This estimator is always positive. So even if tau square, the true tau square is equal to 0, you will always get a non-negative or a positive estimate using the Sittig-Jonkman estimator. So that simply means when tau square is large, you, let's say, overestimate your tau square with the Sittig-Jonkman approach. But whether it is important or not, the kind of estimate you use and the properties these estimators have, we will just discuss, or we'll discuss it later on in one example. So here's just the idea of the Pauli-Mandel estimator, because it's a relatively, or it's related to the Cochrane statistics. So instead of the fixed effects estimator like in Cochrane's Q, we use here the random effects estimator with tau square as a parameter. And we also use, instead of the weights from Cochrane's Q here, the weights for the random effects. So that is simply a function of tau square. And then this simply the idea is that we try to find a solution of this equation. Here you will find tau square such that this quadratic form is equal to k minus 1. And this solution is called the Mandel-Pauli estimator. And the solution is unique and exists given that Q at point 0 is larger than k minus 1. If Q at point 0 is less than k minus 1, then you cannot find a solution here of this equation. Then the Pauli-Mandel estimator is set to 0. The Pauli-Mandel estimator is identical to the empirical Bayes estimator, though the derivation of both estimators first seems to be completely different. But finally, it turns out that these estimators are identical. And then the question is, which heterogeneity estimator should we use? And there is no paper by Veroniki and co-authors in 2016. They looked in a lot of papers where the properties of the heterogeneity estimators were discussed. And finally, they recommend the use of the Pauli-Mandel and the restricted maximum likelihood estimator of tau square. Though all the other estimator here in certain sense also have their justification. And for instance, in the biomedical literature, biometry literature, the Der-Simon and Laird estimator is still the estimator mostly used. And of course, here's a question I've already posed, that does this choice of the heterogeneity estimate affect the statistical inference on the fixed effects? That's a question we will give an answer in some minutes. So one of my contributions to the meta-analysis theory is given here on this slide. It is in the random effects model. What we have discussed up to now is this kind of approximate standard 1 minus alpha confidence interval that we have as a center of the confidence interval, the random effects estimator plus minus the standard error times the critical value from the standard normal distribution. And we have these variance estimator here. These estimates, or these confidence intervals, let's say, has two things which can be improved. Of course, the standard normal quantile here has only is only good when the number of studies is large, because it's based on asymptotic theory. So in a paper of 2001, Hartung and May, we proposed another confidence interval, and independently Sidik-Jonkman proposed the same confidence interval. So I will call it the Hartung-Knapp-Sidik-Jonkman interval, or shortly HKSJ. And instead of the quantile of the standard normal distribution, one can use the quantile of the T distribution. There is also some kind of theoretical justification for it. And what is known here is also that the standard error given in this form, or the variance given in this form, underestimates the true variance of these estimator here, and you get a better variance estimator using this form here. So that alternatively to the standard, let's say, standard confidence interval we have already seen, so you can also use the Hartung-Knapp-Sidik-Jonkman interval, and this is the interval now which is recommended compared to the standard, let's say, confidence interval when you do the meta-analysis up to the point we have already discussed just in these generic models. Some remarks: when you look at the length of the two competing confidence intervals here, the standard one here, the Hartung-Knapp-Sidik-Jonkman, these are the differences, and often the length of the Hartung-Knapp-Sidik-Jonkman interval is larger than the length of the standard confidence interval. But that is not always the case. It's also possible that the length of the Hartung-Knapp-Sidik-Jonkman interval is smaller than the length of the standard confidence intervals. And this is the case when the number of studies is reasonably large, so that there is no big difference between the critical values here, and when the studies are quite homogeneous, so that they are, let's say, close to a fixed effects model, because in this situation here, the sum becomes very, very small. And a kind of ad hoc modification to ensure that the Hartung-Knapp-Sidik-Jonkman interval is always larger or equal to the length of the Hartung-Knapp-Sidik-Jonkman interval is always larger or equal to the length of the standard confidence interval, is that we take the maximum of 1 and these, let's say, weighted empirical variances. And then there is also another effect when we use the Pauli-Mandel estimator for tau square. So then we always apply these ad hoc modification, because the Mandel-Pauli estimator is a solution of these equation here. So that maybe when you look at the recommendation here from the Veroniki paper, given the Pauli-Mandel estimate, or use the Mandel-Pauli or the Pauli-Mandel estimator for the heterogeneity parameter and applying so the Hartung-Knapp-Sidik-Jonkman interval, you will always use these, what I've called here the ad hoc modification. So, and in the R package meter, so there is an option, Hartung-Knapp equals to true, so that you will get the Hartung-Knapp-Sidik-Jonkman interval in the metagen function. So some comments to the application here of the random effects model. As you know now, if tau square is equal to 0, we have the fixed effect model. Is tau square positive? We have the random effects model. And usually what we have, well, based on the ideas we had for the statistical analysis, Yeah, we borrowed, let's say, all the things from one-way random effects analysis of variance model. Yeah, where we have the unbiased estimator of the means. Yeah, we have the estimates of the standard errors of variances, and the estimates of means and variances are stochastically independent. What we do here in meta-analysis, as I've already said, the analysis is always conditionally on the observed variances or estimated variances of the parameter estimates. Yeah, so that there is also statistical uncertainty in the parameter, and the variance estimate is simply ignored in meta-analysis. Yeah. There might be a possible correlation between the effect size estimate and the variance estimate. Not for the mean difference, but I will show you in the next slide the standardized mean difference, for instance, as example, and you will see that there is a correlation between the estimate of the effect size and the estimate of the variance of these effect size estimator. Generally, we do not assume or we do not have unbiased estimator, for instance, for the log odds ratio or log relative risk, when we have maximum likelihood estimator, they are not unbiased in general. And we have two unknown parameters here in the random effect model, which we have to estimate. That is the average effect size theta and tau square. So that was the kind of the general part. Before we go to some further theoretical considerations, I've just included here in our program for the secondhand smoking, just to show you, given the data set here, how you can then on the log scale calculate the standard error with the formulas I gave you on the slides. Let's say 10 slides before. And then when you have the log and the standard error of the log relative risk, you can then in the R package meter again apply the metagen function, with the first argument, the log relative risk, and as a second argument, the standard error of the log relative risk. So what you do here is then you do the meta-analysis on the relative risk scale. So on that we will see here, here first on the meter 1 object and the meter 2 object. We will use the Hartung-Knapp-Siedik-Jonkman interval. And there is a possibility to back transform the results for the relative risk to the original scale, given that you say here that the summary measure is the relative risk. So it's just three things I want to show you here. As a result, for this meter 1 objects, the standard we have already seen. Now the difference is only here, the fixed effect is always the same. And the random effects model now is here the Hartung-Knapp-Siedik-Jonkman interval. So we do not have any heterogeneity here. Tau square is equal to 0, so that we get here the same estimates. And so that the only effect here in the difference of the confidence intervals is the different use of the quantiles or the critical values here for the using this standard normal distribution, and here the t distribution with 18 degrees of freedom. So that is also here that the Z stands for the first test statistic and the T for the second test statistic here. P-values are very small, so that the conclusion is the same, so that secondhand smoking affects the lung cancer. Here is nothing more to say the tau square is equal to 0, and also the p-value of the Cochrane's test is rather large. Yeah, and you have here the interpretation. Yeah, what is displayed here? We have the inverse variance method, the decimal-layered estimator, the Hartung-Knapp adjustment for random effects model. Yeah, so and relatively new in this presentation is also now that there is a confidence interval for tau square and tau based on a method proposed by Jackson. Yeah, but I do not have included, I didn't include any confidence interval for tau square here in my slides. And now the important thing is that you have to compare the two slides here. What is the meter 3 and what is the meter 2 object? There is only a small change. Yeah, here are the results for the log on the log scale, and everything is done here on the log scale. And when you do retransforming the results, whoops, wrong direction. Yeah, only the estimate and the confidence intervals will change. So these are now the results on the relative risk scale, so that the relative risk is 1.42. Yeah, getting lung cancer by secondhand smoking with these confidence interval. The rest of these output remain the same. Yeah, so that these Z and T, the T statistics, yeah, are not calculated, let's say here, relative risk divided by some standard error. It's still the log relative risk divided by the standard error of the log relative risk. Yeah, and all the analysis here for the heterogeneity is for the relative log relative risk that you have to keep in mind when you back transform the results, and that meta-analysis is done on the log scale. All the results here in the meter 2 object are on the log scale, and only the effects and the confidence intervals, by using the exponential function, are then back transformed to the original scale, the relative risk. Yeah, so that's sometimes not so easy to see what's really happened in the different objects or in the different analysis in the R package. Yeah, when you immediately start with the summary here, maybe it's not so easy to recognize that these are the result or for the log scale. So here's now an overview of certain functions in the R package meter, which you can use. We have discussed the metagan functions already. That is for the generic inverse variance meta-analysis. That simply means you need the estimate of the effect sizes and the corresponding standard errors. Like in the first example where we have calculated the difference of the means and the standard errors, we have done the calculations on our own. You have to know the formulas. Yeah? But sometimes it's not easy to remember or recall all the formulas. And why should you look in there, let's say in books or something like that for the formulas? You can implement the formulas. And for instance, for the continuous outcomes, and you have something with means, difference of means, there is in this R package the function metacont. I will show you now in the next slides how you can apply it. So it's not necessary that you know how to, let's say, especially how to calculate the variance or the standard errors of the effect size estimates. Everything is implemented here. For the binary outcome, there will be the function metabin. For metacore, it gets, or for the correlation coefficients, there is the function metacore. And these two First functions are always uses the comparison of two groups, but you, of course, you can do the meta-analysis also for single means, single proportions, or single incidence rates, and you have here your own functions. Yeah, tomorrow we'll also discuss the meta-regression function, and we have already seen the funnel plot. Yeah, these three functions I will not discuss. And tomorrow also for assessing publication bias, we will use the funnel and the meta bias function. Yeah, but just here an overview of possible functions you can use in the R-package meter. Alternatively, you can use the R-package meta 4. There are not so many, let's say, functions for the meta-analysis. The important thing here is that there is a function effect size calculation. And with these effect size calculation function, you can compute for a lot of data situations the effect sizes, and you will get the sampling variances. Yeah, so not the standard errors, yeah, but the square of the standard errors. So that's very important. Yeah, so the standard you use in meta 4 is the sampling variances, whereas in the meta package you have to use the standard errors. Yeah, so and the general function here is rma.uni, so that you do the meta analysis via linear mixed effects models. That's nearly the same than the inverse variance method, the notion used in the R-package meter. Yeah, and there will be some other functions here available. We will just go tomorrow also a little bit in detail here for this meta-analysis of generalized linear fixed effects. Yeah, but you will get an idea of the Mantel-Haensel method and Peto's method too. But here I will use the implementation of the meta package to show you the results. Yeah, and also I have the forest plots and the funnel plots also in these package. Sometimes it's given the data you have and you want to calculate the effect size estimates and the sampling variances. Yeah, you can use really this function effect size calculation because there are a lot of effect sizes implemented. Yeah, so that's not complete. Yeah, so for, let's say, for dichotomous variables, 1-0 variables, yeah, you can calculate the log relative risk, the log odds ratio, the risk difference. Yeah, so for event counts, you can use the log incidence rate ratio or the incidence rate difference. For the quantitative variables, for instance, the mean difference, the standardized mean difference. There's also now the ratio of mean difference possible. For variables of or measures for variable association, yeah, as the correlation coefficients or the phi coefficients, and so on. Yeah, you can look into the documentation for the Pascal function to see that a lot of effect sizes can be calculated with this function. So, and now I will discuss a little bit on effect sizes based on means. And maybe when I'm done with this part, we can have the next question and answer session. So what we have already done or considered is the difference of two normal means. Sometimes one uses a standardized difference. So slightly a different notation to the example before, now mu1 and mu2. So that not experimental or control, it could be everything. And the true variances are sigma 1 square in the first group and sigma 2 square in the second group. And the parameter of interest now is the standardized mean difference. So that means mu1 minus mu2 divided by sigma. Yeah, what is sigma? Sigma could be when you assume that the two variances here are identical, it would be a kind of a common standard deviation. If you cannot assume that these two variances are identical, yeah, let's say it's a kind of average of the population standard deviation. Yeah, so an average of sigma 1 and sigma 2. So what is the advantage here of these estimate, or sorry, these parameter? They have in their numerator and denominator the same unit. Yeah, so that is a scaleless parameter. Yeah, maybe you measure something in meters, yeah, or kilometers, and something else in miles. Yeah, you do not have to transform the miles to kilometers or vice versa. Yeah, you can simply use the data and use the standardized mean difference as an effect size because it's a scaleless parameter. Yeah, and especially in the social science or psychology, yeah, they often use the standardized mean difference, yeah, because they have to deal with different units and different studies. So given now, or you are interested in estimating now these effect size, how do you estimate it? And of course, in each of these groups, you have to have the information, you must have the information about the sample mean and the sample variances. And one possibility is the estimator D we have already seen in one example before, that is called the so-called Cohen-Dean D. Yeah, so that's simply the difference of the sample means divided by S. Yeah, and S square is nothing other than the maximum likelihood estimator of a common variance under normality. Yeah, so that's all. So that under normality, this D is the maximum likelihood estimator of the standardized mean difference. Yeah, so that would be that is one possibility how you can estimate it. Yeah, and of course you know that under assumption of normality, yeah, this S square is now not an unbiased estimator for a common variance. Yeah, so the estimate of the common variance is here number of the sample size -2. Yeah, and you can use this estimate 2 here. And in the literature, in the behavioral sciences, psychology, this estimator is denoted by G and known as Hedges G. Yeah, so so these here is the unbiased estimator under the assumption that we have a common variance in the two groups. And I've already discussed in one of the slides before about the assumptions we are a little bit ignoring. And here you can, so that's the first example here where we can demonstrate it. When we have calculate the expected value of these hedges G, yeah, so it's the standardized mean difference plus something else. Yeah, namely 3 times
the parameter divided by 4 times the total sample size minus 1. This is kind of approximation. So that simply means that the estimate here, hedges G we have, is not an unbiased estimator for the standardized mean difference. It's a biased estimator. And the second point here is that when we calculate the variance, we can approximate the variance in this form here. And the important thing is here that the variance of G, so the true variance of G, depends on the effect size of interest here, the standardized mean difference. So when we use this estimate here, hedges G, it's a bias estimate. And when we want to estimate the variance of G, of course, then we have to plug in here the estimate of hedges G. So, and consequently, the estimate of G and the estimate of the variance of G, these are not no more two stochastically independent statistics. There is a dependence. In case we have this assumption of equality of sigma 1 square and sigma 2 square, we can do some kind of the calculation here that we can show that the estimate here follows a central non-central T distribution with a certain non-centrality parameter. And we can use the results simply to modify a little bit our estimate. Because we can here, instead of the approximation, we can also directly then calculate the exact expected value and the exact variance of hedges G. So the exact value here of the expected value of G is given in this form here. So we have this multiplicative before the standard mean difference. So that's the gamma functions here. And the same for the variance of G, where we also have again this theta to the square here. So the important thing is then that knowing these expected value of G, we can modify our G in such a way that is an unbiased estimator. Simply take now the inverse of this constant multiplied by G. In the literature, let's say in the old literature, because of the gamma functions here, you can also find these estimate here that is so nearly unbiased or approximately unbiased estimator, because this formula, this constant here, can be well approximated in this form here. So, and with this G star, we can also get the estimate of the variance with G star, and we plug in here just the hedges estimator, not the corrected one. So it's a little bit of play with different estimates, what you can do here for the standardized mean difference. So in the large sample confidence interval then is just given as G star plus minus the square root or the standard error of G times the critical value of the standard normal distribution. So this is an example where, starting with just G, hedges G, we do not have an unbiased estimator, and we have a correlation between the estimator and the variance of these estimator. For the bias, we can do some kind of correction. but we still have the correlation between these two estimates. Yeah, but there are some studies that this correlation is not very large. So that is, you can accept that you can ignore the correlation between the effect size estimate and its variance estimate. So, and when it is necessary to use this kind of unbiased standardized mean difference, just looking, and that's because I've used here this approximate formula, it's easier to see the effect compared to the effect here with the gamma functions. Yeah, so when it is this constant different from 1, so it's different from 1 when what you subtract here is, let's say, relatively large, and if the sample sizes are relatively large in all the studies, yeah, so the 3 over what's given here in the denominator is relatively small, yeah, and here it's just for some values, yeah, when your total sample size is 76. That's some examples for the standardized mean difference. Yeah, you will see here a difference, yeah, on the second digit. Yeah, in all the other cases, yeah, you do not see a relevant difference. So it's of course implemented in the R packages, these unbiased standardized mean difference, but you should also only use it, or it's necessary to use it when the total sample sizes are relatively small in the studies, whatever relatively small means. So let's go back to the amlodipine example. We have already analyzed it with respect to the mean differences, and we can now analyze it with respect to the standardized mean difference. And so the question is really, do you want to do the programming here on your own? So to calculate G star and the variance of G star, or the variance of G, whatever you will use. And or will you use some functions in the R package? And of course, you want to use some functions in the R package. So when in the R package meter, you can use the metacont function. So that's simply the function for continuous outcomes like the mean or the standardized mean difference. And you can simply use these metacont now. So we have the sample size, the sample means, and the variances here in my notations, N1, X1, and var1 for the first group, and N2, X2, and var2 for the second group. And then the arguments here in the metacont function is, first you have to give the results for the first group, sample size, means, and again now standard deviations, that's important. And then you have to give the results for the second group, sample size, means, and standard deviation. And then you have to say now in this metacont function, which effect size you want to use. And its SMD is the standardized mean difference. Oops. And when you want to use the Hartung-Knapp confidence interval, Hartung-Knapp-Siddiq-Jonkman confidence interval for the random effects meta-analysis, you have to specify that HIKN is equal to true. So and that would be the result you get. Again, a result with respect to fixed and random effects model that you get the same conclusion. Also for the standardized mean difference here. So again, like for the mean difference, the effect size estimates in the fixed and the random effects model are relatively similar. You get the confidence intervals, test statistics, and the corresponding p-values. So that you can conclude that there is a significant difference between amlodipine and placebo. The estimate here for the decimonial estimator is just 0.02. That's smaller than, or it's a difference value than, of course, than for the mean difference. And we have here a situation for the standardized mean difference that the test of homogeneity yields a p-value of nearly 20%. Recall that it was 9% only for the mean difference. So that based on, let's say, the choice, what you want to have is, or want to use is that the standardized mean difference in this example seems to be a effect size where it is more homogeneous, the results, than for the mean difference. And sometimes there is some, because meta-analysis is retrospective, you can decide, given the data here, which effect size you use. Sometimes it's important that you can easily interpret the results. Maybe the difference of means is easier to interpret as the standardized mean difference. But on the other hand, sometimes there is some considerations that you want to use an effect size such that the estimates are as homogeneous as possible. So, and when you are going to the second part, then you would use here the standardized mean difference instead of the mean difference here. So the final conclusion here for mean difference and standard mean difference, standardized mean difference, of course, it's the same. The treatment is better than control. So, and the standard here is that when you do the analysis given in this form here, just that you say SM summary measure is equal to the standardized mean difference, that you will get hedges G, the biased corrected standardized mean difference. So, and that is the formula G star we have here on this slide. Of course, in this function, metacont, so there are several further options you can use for the standardized mean difference so that you can also get Cohen's D, the not corrected bias estimator, and also the exact estimator. And for the Hatton-Knapp-Siddig-Jonkman interval, of course, it's again a little bit wider, the confidence interval here, because of the T distribution and the different standard error. So the p-value here is a little bit larger, let's say, than the p-value here in the random effects model before in the standardized analysis given here. But of course, it does not matter which kind of analysis do you do here. Also to each of the usual type 1 errors you choose, you will get also with the Hatton-Knapp-Siddig-Jonkman interval or approach a significant result in favor of the treatment amlodipine compared to placebo. And again, you have here the information what's given on here. So heterogeneity statistics are the same as on the slide before. So, and here is some, in this example, some, or on this slide, some a demonstration about the effect of tau square on the estimate of our parameter for the fixed effect. So I've used here several estimates. The testimonial layer, the hedges, the maximum likelihood, the restricted maximum likelihood, and the Selig-Jonkman estimator. And when you look here at the different estimates of the heterogeneity parameter, yeah, you see a little bit of variation. So the maximum likelihood estimator, maybe when you're a little bit familiar with the estimation of variance components, maximum likelihood estimation is not really recommended because you underestimate usually the true variance. So the 0 is not an unusual estimate. But the restricted maximum likelihood estimate is only a little bit larger. So 3 times larger nearly is the testimonial layered estimator. And also let's say roughly 3 times larger than the testimonial layered estimator are the hedges and the Selig-Jonkman estimator for tau square. And when you look at the estimate now in the random effects model for the standardized mean difference, yeah, you see a little bit of variation here given the different estimates here. But it's not, I would say not so much different that you have to worry about your results. What is a little bit different here is when you look at the standard, I've called the standard confidence interval, yeah, so that the length of these confidence intervals are rather different, let's say. Yeah, so of course we get the smallest confidence interval for the maximum likelihood estimator because this is simply the fixed effect confidence interval. And of course, the larger the variances, the wider the confidence intervals. Yeah, but for the large value of, let's say, large values of the estimates of the tau square here, yeah, hedges and Selig-Jonkman, we get the largest confidence interval. And of course, there is a little bit of difference whether you say that is between 0.26 and 0.58, or it is between 0.16 and 0.68. Yeah, so there is a certain effect of the estimates for the heterogeneity parameter on the standard confidence interval. When you look at the Hartung-Knapp-Selig-Jonkman interval, yeah, you do not have this, let's say, variation. Yeah? So it's less variable, yeah, the lower and the upper bound. So that sometimes in some, I think it's Selig-Jonkman said that, yeah, so this interval is, let's say, a little bit more robust against the choice of the heterogeneity parameter than the standard confidence interval. Yeah. So, and why it is so that there is some robustness against the heterogeneity estimator, I do not have an explanation. I've met one guy, did this PhD thesis also investigating this kind of robustness, and but here also he couldn't tell me what is really the reason for these, let's say, relatively robust results you get with the Hartung-Knapp-Selig-Jonkman interval with respect to the different estimators for tau square. Yeah? So when you look here at the results, yeah, I think it's not really necessary to get a kind of recommendation which estimate you should use. Here just an example now for how you can use the SCAL function in meta4 to do the meta-analysis in meta. So that's the part here. I've already told you that these effect size calculation function You can do a lot for different estimates. So I've used here the mean difference, and here a little bit different, the number of or the order of the arguments here. But the good thing is when you get these or use this function in the R package meta 4, yeah, you will get an estimate, and in the data set that is called yi, and the variance estimate, which is called vi. Yeah, and then you can go to the meta package and, for instance, use the metagen, yeah, with the results from the data set here, that one from the meta 4 package, to do the meta analysis. Yeah, so that's an alternative you can use for doing meta analysis. Yeah, so in this part is especially useful when I now go a little bit back to the different functions in the 2 package. So here are several functions implemented for, or here are several effect sizes implemented in different functions. But in this function here, in the effect size calculation function, more effect sizes or estimates for effect sizes are implemented. And when you cannot find the effect size in this meta package, yeah, it's simply possible to do the calculation here in the meta 4 package. Yeah, and maybe then you can go back to the meta package if you like. If not, you can also use the RMI function, and I will show you some results later on for the RMA function in meta 4. So here are the results in meta 4. And that really depends whether you, let's say, not really like it or not. So I like a little bit more the meta package because you get the results for the fixed and the random effects model simultaneously. And in the meta 4 package, you just get the results for one model. Yeah, so, and you have to decide when you use the function armr.uni, yeah, which model do you want to use? So no options really here. So, and then you get the estimation that, yeah, so the default model is always a random effects model, and the default estimator for tau square is always the restricted maximum likelihood estimator. Yeah, and then you get the estimate of tau square. Yeah, the random effects, the restricted maximum likelihood estimator, with a certain standard error, and also the square root of the estimator, so that you have an estimate for tau, I square and h square we ignore. Again, it's the test for heterogeneity is Cochrane's Q. We have already seen the result that for the mean difference, yeah, it's 9%. Yeah, and you get here the standard results for meta-analysis, the estimate, the standard error. Yeah, and now it's important to look whether it's the standard confidence interval or the Hartung-Knapsey-Jonkman interval, which also implemented in this RMI uni, whether it's a set value or it's a t value. Then we have the p-value for the test, yeah, and also the confidence interval with the lower bounds and the upper bounds for the mean difference. Yeah, so that's the other R package I want to show you. Okay, so that was the part I wanted to show and discuss with you in my second lecture for today, and maybe there is some time for question, answers, or discussion now.
Yes, thank you, sir, for another very wonderful session. And we are opening for discussion now. So if you have any question, if anyone has any question, either they can raise hand or they can write the question in the chat box. Anyone? Till we get any question from the audience, I have one question regarding the HKSJ estimator. So can we understand that the HKSJ confidence interval will be more reliable in a situation where there is more heterogeneity between the true effect sizes of different studies which have been included?
Yeah, so so that's a good question. So I do not have any simulation results here. Maybe. So there is also some kind of papers now when you are in the situation doing the random effects meta-analysis, that the recommendation is to use this HKSJ interval. But it's not really that you can generally answer the question. The performance of the intervals always depend on the parameter of interest. For instance, for the standardized mean difference, there's nearly no difference between the standard the standard confidence interval and the Hartog-Knapp-Siedik-Jonkman interval. For the mean difference, there is a difference, because the standard interval is usually too short. So, and the Hartog-Knapp-Siedik-Jonkman in simulation studies, it was shown that it has a better coverage probability. But it always not so that's a kind of, let's say, general recommendation that you can find in the literature. Also for the binary outcome, I will give you some information in the last section, lecture for today. But it always depends, as I said, on the parameter or on the effect size. In our papers, we have just shown that with our interval in general, we are closer to the nominal significance level. It does not mean that we control the nominal significant level, but we are closer to the nominal significant level than the standard confidence interval. So that's very important that you have to keep in mind.
Thank you very much.
Website पे advertise दिखाया है ना, young professional का.
So sorry.
Yeah, sorry, there was some noise. So there's another question, but I think you have already covered that in your lecture. So the question is how we interpret results of meta packages. So in the lecture itself, you have in a very elaborate way, you have discussed the interpretation. But if I request the person who has asked the question, if you have any particular result you want to ask how to interpret that, then you can ask that. If you have any particular point, because Professor Knapp has already discussed it very elaborately.
Yeah, so the important thing just for the interpretation is, that's it why I like a little bit this meta package more than the meta 4 package, that you get some kind of information here at the bottom always, what has been calculated. And of course, so the main result for the meta-analysis is always given here for the fixed and the random effects model. Yeah, and here you have some additional results for the heterogeneity parameter. And there's always a discussion whether it's important or not, because also from the, let's say, mathematical statistics point of view, you can also say that tau square is a kind of a nuisance parameter just in the analysis. Yeah, so the important thing is the results here of the fixed and the random effects model. Yeah, and then simply it depends on the, maybe that would be some kind of question, the interpretation. So here it is, you have to say what is this, let's say the null hypothesis. When you have the standardized mean difference or the mean difference, yeah, so the hypothesis would be that the parameter is equal to 0. And you have to look whether 0 is here inside. When you, so when I've discussed the back transformation, somewhere lost, where I had this second-hand smoking. Yeah, so when we have here the second-hand smoking, of course, that's a little bit different. Yeah, so that we have, and that's, so maybe that's a really not easy first to understand what's going on here. Yeah, we do here the analysis on the log relative risk scale. So I will talk about log relative risk in the next lecture. And that would simply mean that the null hypothesis is that the log relative risk is equal to 0. Yeah, and whether you can reject or not this null hypothesis, you have to look at these confidence intervals, whether 0 is in the confidence intervals or not. Yeah, and when you go to the back transformation, the relative risk, so the relative risk is P1 divided by P2. Yeah, that simply means that the two groups are identical if the relative risk is equal to 1. So that's the null hypothesis then. And you have to look whether 1 is included in this confidence interval or not to reject the null hypothesis or not. Yeah, and again, yeah, when we are already here on this slide, yeah, all the other results here are not for the relative risk, they are for the log relative risk.
Thank you very much, sir. There is one query from one of the participants, A.B. Thomas. And the query is that are these results from the dataset Kerala, and whether you'll be sharing the presentation slides with us. These are the two queries from the participants.
So I do not completely understand the question. Yeah. So on the Kerala, on the website, yeah. With all the Kerala material, you already find everything what is here in my presentation. So that's, let's say it's a kind of a shorter presentation, but of course you can share the slides here. Yeah, so the only thing what is different is when I go give this workshop in presence, I did also some kind of R demonstration. So, and the only thing now I've done for this workshop is that I have included the R programs here on my slides. Yeah, so in the website on the Kerala, you will find the data sets, you will find the R program, and you will find all the slides I've used in the Kerala workshop. And these are only a part here, what we have here on the of the Kerala workshop. But of course, I've sent you the slides, you can share it with everyone, no problem.
Thank you very much, sir. Anyone, any other question related to the present session? So I guess there's no more query right now. So we can call off the session and we'll meet again at 3:30 p.m. by Indian Standard Time. That is approximately half an hour
Yep.
post this session. Thank you so much, sir. It was really interesting and very enlightening also. Thank you.
Thank you.
So welcome back everyone, and we are about to start our final session for the day. And those who are in academics, they know how difficult it is to take 4.5 hours lecture in one day. So we are really thankful to you, sir. Okay. Someone is unmuted. Okay, so it's actually very inspiring to see you all energetic even after taking 3 hours of lecture. And so whenever, sir, you are ready, you can start with your lecture.
Okay. So before I start with my last lecture for today, I just want to make a short comment. I've done my usual typo here. So after Dortmund.de is missing. So the website is www.statistic.tu-dortmund.de, and this DE is missing here for the link to the Kerala slides. Yeah. So, and after today's lecture, I will also upload here this presentation on the website. So sorry for the typo. So here in the last lecture for today, I want to talk a little bit about controlled clinical trials with binary outcome. So the reason is why I want to talk a little bit more in detail about this topic is there are several effect sizes you can use. And also when we have 2x2 tables in the studies, we can also do some statistical meta-analysis beyond the generic meta-analysis model methods like fixed and random effects model we have discussed today. So just a little bit, some formulas at the beginning. So we consider again K independent trials, comparing now a treatment and control. And the outcome simply is binary, success or failure, for example. And with PTI, I will denote the success probability in the treatment group, and with PCI in the control group in the ith study. Sorry. So, and when we get the results in each study, we can use a kind of 2x2 table to show what has happened. Yeah, so that we have the number of successes and failures in the treatment group, and in the control group. So here the 1 stands for success and the 0 for failure. So that's a connection now between these success probabilities P and what we have observed in the ith study. And there are several effect sizes possible for this binary part. First of all, we could use a difference, which is then called the risk difference in some areas, or probability difference. PTI minus PCI in the ith study. So then the relative risk, I've used this notion several times already today. So that's simply the ratio. So PTI divided by PCI. Then we have the odds ratio. So the odds in each study is PTI, or in each group is PTI divided by 1 minus PTI. And then you build the ratios of the odds. So that the odds ratio and given in this form. So I will discuss these 3 effect sizes. I just want to mention this variance stabilizing transformation with the arcsine of the square root of PT. This variance stabilizing transformation has mathematically, statistically the advantage that the variance estimator just depends on the sample sizes and not on the effect size. But the arcsine difference, how it is sometimes also called, is difficult to interpret. Risk difference, relative risk, and edge ratio are easier to interpret, and so I will restrict my presentation to these 3 effect sizes. And when you had appropriate estimates of these effect sizes and standard errors, we can do the generic inverse variance method in the fixed and the random effects model we have already discussed today. So, and it's easy to start. How do you estimate such kind of success probability? You simply look how many patients you have in your treatment group and how many successes you have there. And with this relative frequency, you estimate the probabilities. Before we start with further estimates and formulas, I just want to discuss with you one point again a little bit. So in the example from amlodipine, we have already discussed with this mean difference and the standardized mean difference. Maybe that one can choose the effect sizes in such a way that they are as homogeneous as possible. When you look simply now for the binary thing and look at the probabilities, we can calculate here the following. Assume that in both studies, the probability of success in the treatment groups is 0.6, and in the control group, it's 0.2. That simply means that the difference of the probabilities is 0.4 in both studies. When we take the ratio, we get the relative risk equals to 3. When we calculate the odds ratio, the theoretical one, it's 6 in both studies. So it simply means that the true effect sizes will be the same if in each of the studies the treatment probabilities will be the same and the control probabilities will be the same. So that's a stronger assumption than you just considering the homogeneity of the effect sizes. And we can introduce some, let's say, heterogeneity of the effect sizes when we change in some of the treatment or control groups the probabilities. So now assume that in the second study, instead of 0.6, first study, we have 0.7 for the treatment in the second study. And in the control group, instead of 0.2, we have 0.3. Then the risk difference in both studies are identical. So analyzing the data from these 2 studies, and these are the true parameters, a fixed effect model would be the correct one. However, for the relative risk and the odds ratio, the true parameters will be different. So that will be the case of the random effects model. So that simply means that the choice of the effect sizes may introduce heterogeneity in your analysis. Of course, you do not know in practice what are the theoretical success probabilities. It's just for demonstration purposes here, and maybe you can check when you use the different effect sizes yeah, for which effect sizes maybe the study results are as homogeneous as possible. Alternatively, one could think about a bivariate approach. Here, that simply means when you have the 2x2 tables, yeah, maybe that you have a multivariate analysis. Yeah, so just looking at the pair here with the estimates for the probabilities in the case studies. Yeah, but this would go in the direction of a multivariate meta-analysis, which is not the topic of this lecture. So now simply some formulas and with some comments whether everything exists or not. Risk difference is relatively easy. We can estimate it, as I've already said, with the difference of the relative frequencies. Yeah, we have the number of successes in the treatment group in the I studies divided by the total sample size of the treatment group in the I study minus the same for the control groups. Yeah, and then when we calculate the variance of these estimator and estimate these estimator, we end up with these formula here, which just depends on the sample sizes. And the only thing is when you think about the now inverse variance method, we have to take the inverse of these estimator. Does these inverse always exist? Yeah, and you only have problems, yeah, when you calculate here some zeros. Yeah, so in these situations given here in this last line, then you will get some problems for calculating the inverse. Yeah, but normally you do not have so many zeros in your study. Within the binary data meta-analysis, for the fixed effect model, there is always an alternative. Originally developed for the odds ratio, there is a Mantel-Haenszel approach. And this is an alternative to the inverse variance method for the fixed effect model. And I've just put here some of the results. It's not important that you now understand everything what's going on here, just some formulas. But the important thing is that you have to keep in mind that the Mantel-Haenszel approach is an alternative in the fixed effect model and has nothing to do with the random effects model. And one possibility to do the formulation for the estimate, the overall estimate for the Mantel-Haenszel overall studies is given in this form here, a sum divided by another sum. Yeah, but you can also give these estimate as a weighted average of the study-specific ones. Yeah. So, and the question is simply where we find these weights here, and the weights are the inverse of the variance of the risk difference estimator in the study. Yeah, and now there is a certain assumption when there is no difference between treatment and control. Yeah, so that simply means that the true risk difference or probability difference is equal to 0. Yeah, and the true underlying probabilities are the same in all studies. So there are some further assumptions for calculating here these weights, and these assumptions are still stronger than the assumption of the usual estimates or weights we have in the fixed effect model. Of course, one can also calculate asymptotic variance of these estimator, so that we finally end up with these confidence interval for the Mantel-Haenszel approach for the risk difference. Yeah, so once again, it's not important that you completely understood, or do you understand that you understand the formulas now? That's just an idea that, well, it's important only that the Mantel-Haensel estimate approach is an alternative to the fixed effect model. One can also display these estimate as a weighted average of the study-specific estimates, and the weights are chosen under certain assumption. The important assumption first is that there is no difference between the treatment and the control. So then there is a relative risk. Of course, you can do the same, starting with these p hats, just say p hat divided by pt I hat divided by pc I hat. Yeah, and there are some theoretical justification to add 0.05 to this estimate. Sometimes one use it, or sometimes not. So on this formula here, I have used the additional increment of 0.5. The advantage is that this estimate then always exists. Otherwise, when you have no successes in the control group, you will have a 0 here in the denominator, and you will have some problems. You can also calculate the variance. Now that's important on the log scale for this estimator. And we have already discussed it, or I've briefly mentioned it, that for the relative risk, we will do the meta-analysis on the logarithmic scale, and the variance of the logarithm of these estimate can be estimated in this form. So that is 1 over the number of successes in the treatment group minus 1 over the total sample size in the treatment group, plus 1 over the number of successes in the control group, minus 1 over the total sample size in the control group, whether now you have 0.5 or not. For the variance estimator, then also beside that NCI 1 could be 0. It could also be that the number of successes in the treatment group could be 0, then it would not exist. This estimator, so that it's the increment of 0.5 guarantees that the estimate of the relative risk as well as the estimate of the variance of the logarithm of the estimator always exist. So there is also especially for the relative risk estimator, justification given by Cox. So the question simply is, which amount should I add to these values here such that the estimate has a minimum mean square error? And then the solution is really that you have to add 0.5. So when you have calculated these, you can do the inverse variance method on the log scale, combine the results and back transform it then to the original scale. So, and now it's important. Maybe let's look at this situation here. When we change the role of what we are interested in, not the success probabilities of 1, but the success probabilities of 0. So then these variance estimator did not change or will not change. However, these variance estimator will change because here we have the total sample sizes in the treatment and in the control group. And then instead of the number of successes here and there, we will include the number of failures here and there. And then we will get another variance estimator. Yeah, so it simply means that, yeah, you have to keep in mind that the variance estimator will change when the role of success and failure changes. Yeah, and we will discuss it a little bit later. Yeah, and of course, if 0.5 is not always added, we will use these estimate. Yeah, and we will see in the R packages that there are, so let's say, two different strategies. Yeah, so the standard strategy is this one here, that we only add 0.5 or another constant when there are 0 events in the group. And alternative is that you always add this increment of 0.5 in all cells of your 2x2 table. Yeah, so these, again, you have to keep in mind that there are two different strategies. Yeah, and of course, here is also a Mantel-Haenszel approach as an alternative for the fixed effect model. Yeah, and here is just given the formulas. Yeah, again, it's only important now that you have to keep in mind that, like for the Rex difference, yeah, also for the relative risk, there is an alternative for the fixed effect model. Yeah, and again, the variance here is on the log scale. And first we do then the combination on the log scale for this Mantel-Haenszel approach. And then we will do a back transformation to the relative risk scale. So, and finally the odds ratio, and there's again the same game. Yeah, either we add always 0.5 given in this formula here, yeah, with these formula there, variance formula, or we only add the 0.5 if there are 0 events in a group. Yeah, so otherwise we use this estimator without adding 0.5. Yeah, so when we add 0.5, yeah, so we get these variance estimator for the logarithm. Of course, when we do not add 0.5, yeah, so there is also no 0.5 in the variance estimate. Yeah, so and it's an easy formula that you can remember that, or always recall, that is 1 over the number of successes plus 1 over the number of failures in the treatment group plus the same in the control group. Yeah, again, the combination, the meta-analysis will be done on the log scale and then the results back transformed to the original scale. Yeah, and note in this situation here, when we change the role of success and failure, yeah, these estimator will always be the same because we have simply 1 over, yeah, the number in the cells of the 2x2 table. Yeah, and you will see it in the discussion later on what will be the effect from changing the role of success and failure in the meta-analysis. So the relative risk is the effect size with some problems. And again, and that is the original one, Mantel-Haenszel approach for the odds ratio. And you can also, can also give it as an weighted average of the study-specific odds ratios. And again, we have here some additional assumptions for deriving the weights. Yeah, so the important one is that the odds ratios are 1 in all studies. So that simply means that there is no difference in the studies between the success probabilities. So there is a long formula for the variance of the logarithm of these estimator, and of course, same procedure as in the previous slides. Yeah, we do the combination on the log scale first and then read back transform it to the original scale. So for the odds ratio, just only briefly mentioned, there's also another alternative in the fixed effect model, the Peto method. Yeah, and it's the idea that you use a scoring method from the likelihood approach. And yeah, so there are still some more restrictions here, and to be honest, I haven't really seen a recommendation for using the Peto method. So also I've given here some arguments for not using the Peto method, but it's also implemented in the R packages. That's the reason, just for completeness, that I mention here the Peto method. Of course, we do not want to do the programming for all these different estimates and variance estimates, and we can simply use in the R package meter, these meter bin function. And so the arguments are as follows. First of all, we need the events in the experimental group and the sample size in the experimental group, then the events in the control group and the sample size in the control group. So then we have to specify which kind of method we want to use. Here I've chosen the inverse variance method. So that is what I've discussed in the first two lectures. And then the summary measure, for instance, the odds ratio. Yeah, so and for the method, we have three different options: the inverse, MH for Mantel-Haenszel, and Peto only for the odds ratio. Yeah, and for the summary measures, we can use the relative risk, the odds ratio, the risk difference, and this ISD, that is the arc-seen difference, that is the variance stabilizing transformation I've shown you, let's say, on my second slide, I guess, for this binary part. So then you can specify the increment. The default value is 0.5, but also you can say, maybe I would just want to use 0.1. Yeah, so there is some not really kind of flexibility, but you can use, let's say, every increment so that the estimate will exist. Yeah, and then there is a logical indicator whether you will use the increment to all cells, or only to the, or only if it is false, then it will only add, if the studies has 0 cell count. Yeah, so that's the play I've described here, always for the odds ratio and relative risks on my slides. So that's first the important thing you have to know for the meta-analysis of binary things. And one important part is especially when we have, let's say, some safety trials in clinical trials. Simply means you are interested in the number of adverse events or serious adverse events. And of course, you hope that in the new treatment, you have less adverse events than in the control group. Or at least that they are the same, but you do not want to have more adverse events in the treatment, in the new treatment than in the control group. And here is a small example only of 3 studies. In the first lecture at the end, we had the question, how many studies do we need? So my answer was 2. And here we have really an example with 3 studies, and that is not unusual in the, let's say, biomedical application of meta-analysis. When you have this kind of data, yeah, you have, let's say, free choice what to do with these meta-analysis. Yeah, do you want an effect size which is additive, that you use the risk difference, yeah, or you want to have a multiplicative effect size like the relative risk or the odds ratio. Yeah. Then of course the usual question you have in meta-analysis, which model would you use, the fixed effect or the random effects model? And of course now when you try to check whether a random effects model would be good, you only have 3 trials. Yeah. And it's not easy to check whether all the effects are identical when you only have 3 trials. Yeah, which method should you use? The standard interval or this Hartung-Knapp-Sittig-Jonkmal interval, or maybe the Mantel-Haenszel interval as an alternative to the fixed effect model, and if this one is appropriate. There are some, let's say, not really criticism, but it's known for the Hartung-Knapp-Sittig-Jonkmal interval that it can be very wide if the number of trials is small. So when I started with working on meta-analysis and seeing some of the simulation results, the minimum number always was 5. So all the paper, the original paper, not 20 years old, on meta-analysis I did with my supervisor, we always started with the 5 trials. And in this situation, it's still okay for the quantiles of the t-distribution. But when you look, for instance, here in the situation that you have only k equals to 3 trials, the corresponding quantile you need would be 4.3. Yeah, and that's more than double than the quantile of the standard normal distribution. Yeah, so that the standard error in the Hartung-Knapp-Sittig-Jonkmal approach is multiplied by 4.3, and in the confidence interval for the standard one, the standard error is only multiplied by 2. I'm not completely sure, but I think when you only have 2 trials and you have the quantile with 1 degree of freedom, it's in this situation around 12. So, and I've copied the program here on my slides just to show you how you can do the meta-analysis with this metabin function. Yeah, so here are the small data. And you can do the standard analysis in, again, this package meta, given in this form here. Yeah. When you want to add 0.5 to all cells, you have to set this logical indicator equals to true. When you want to have the Hartung-Knapp-Sittig-Jonkmal interval, you have to say HKN equals to true. Yeah, and when you have to have both, of course, you have to have to give both options. Yeah, and we want here to do the odds ratio. Yeah. So, and maybe you can look at the forest plot or not. Yeah, and maybe what you can do then is also, yeah, that you may change the estimate for tau. Yeah, so there is also the option, also in the other functions method for estimating tau, that is also method dot tau, and maybe we want to have here the maximum likelihood estimator. Yeah, then you have to go to the help page to see which methods for the heterogeneity parameter are also implemented here. So, and then we can consider the results. So here it is given for the odds ratio, in the program. Now I have done this program run this program for different effect sizes. And let's start with the risk difference and the inverse variance method. Yeah, so we will get these estimates here. That's a little bit a critical situation. Why is it a kind of the critical situation? We have here a p-value of the homogeneity test of 8%. Yeah, when you say, okay, the usual 5% usually used, yeah, I would say I cannot reject the hypothesis of homogeneity. So maybe I can go with the fixed effect model. Otherwise, when you use a higher significance level, you would say, oh, no, we have to go with the random effects model. The effects, the estimate of the effect sizes are small. Of course, adverse events, so the probability shall be small, and of course, then the difference of the success probabilities or estimated relative frequencies are small. Yeah, and then we get the confidence intervals. Yeah, and here we get then the p-values, and clearly for the random effects model, there is no difference between the two groups. Yeah, though the estimate indicates that in the treatment group, yeah, there is maybe a little bit difference in favor of the treatment group with respect to the adverse events. Yeah, while in the fixed effect model, you have sometimes called it borderline significance when you have the 5% significance level. Yeah, so these p-values only a little bit larger than this 5%. So it's not an easy result you get here. And when you choose the fixed effect model and apply the Mantel-Haenszel method here for the risk difference as an alternative to the fixed effect model, you will get a significant result when you have alpha equals to 5%. Yeah, so so recall that the Mantel-Haenszel method is just an alternative to the fixed effects model. Yeah, the results for the random effects model is always this inverse variance method. Yeah, so from this slide to this slide, there is no change for the results. Yeah, but so it's not an easy situation. Yeah, also for the interpretation. And in the beginning, I've already mentioned these handbook or the Cochrane handbook. And there is in this situation when you have small probabilities, so the safety studies in mind, that the Mantel-Haenszel method should be used. That's a recommendation from the Cochrane handbook. Yeah, and when you follow these recommendations here, yeah, you will get a significant result in favor of the treatment. Nevertheless, when you do not have this significant result, you have to keep in mind that the estimate for the risk difference is at least negative. So it goes to the direction that the treatment has less severe or less adverse events than the control group. And that's also first a good sign. Yeah, so, and these are some old style forest plots, but it's sometimes easier to show some of the difference here. Yeah, so we have already, you know already what is a forest plot, that you have the individual effect confidence interval with the estimate of the effect sizes here, and you have the fixed effect and the random effects model. Here on the left side, we have the inverse variance method. Here on the right side, we have the Mantel-Haenszel estimator. Yeah, and you know that the size of the squares here is proportional to the precision of the study. And yeah, you see a little bit of difference here. Of course, the first study is the most important one in both approaches. Yeah, but here is a slight difference. The second study has, in the inverse variance method, less weight than the third study, and here it seems that both of the studies have the same weight. Yeah, so that simply also means that for the inverse variance method compared to the Mandel-Hansel estimate, yeah, it could also be that there is a change of the weights. And it's not this change of the weights like for the fixed or in the random effects model that, so the order remains the same, so that the study with the largest weight in the fixed effects model has also the largest weight in the random effects model, but the weight in the random effect model could be smaller, never be larger than than in the fixed effect model, yeah, up to the end, to the smallest one. Here, it's possible, yeah, that you can also change the order of the weights with respect to the studies. Yeah. So, and here is a little bit the demonstration for the odds ratio. Yeah, you see here a little bit that, yeah, so there is a, not really, so the order remains here the same. Sorry, that's a very inverse variance method. So we have here the fixed effects and here the random effects model. The order is the same, yeah, but larger weight is a little bit downward and the smallest weight is a little bit larger in the random effects model. And when you go to the Mandel-Hansel estimate here now for the odds ratio, so it's not the forest plot from the slide before, you see the change. Yeah, so the first study, which had the largest weight in the random effects model still, and in the inverse variance method before, now has the smallest weight. Yeah. And the second largest now is the largest, yeah, and the smallest is now the second largest. Yeah, and this could happen with the odds ratio or all the others when you use the Mandel-Hansel approach or the Mandel-Hansel method. Yeah, let's say today it's just an observation that it could happen. And it's always difficult to give really a final recommendation for the binary analysis, what you really want to do, or what you really has to do when you have this situation that maybe the fixed effect model is a model you can apply, and which methods then you really want to use. Yeah, and in this situation here, you still have the problem that given the different approaches here, yeah, with respect to the significance level, with respect to the p-values, yeah, you do not get the same result whether you should reject the hypothesis or not. Yeah, and maybe this is a kind of situation where you can say, so one of the points for doing meta-analysis is also that you say, I'm not quite sure, maybe 3 studies are not enough, we need some more information. Yeah, so maybe that you say, yeah, we need more information, more studies to get, let's say, a stable result for these analyses. So this could happen. Yeah. So when you ask me now what I would do with these 3 studies, yeah, of course, it's a safety study. Yeah, it does not go in the wrong direction. It goes into the right direction. Yeah. So I do not. Yeah, we won't say that the serious or adverse events in the treatment group are larger than in the control group. Yes, the only controversy here is whether the number of adverse events in the treatment group is significantly smaller than the number of adverse events in the control group. Yeah, and when you use Peto methods here for the odds ratio, yeah, the p-value is still smaller than the p-value in the Mantel-Haenszel approach. Yeah, so here's just some forest plots. Again, just looking. So now I want to discuss some additional points for meta-analysis of binary data. So we have seen that we can use the inverse variance method for binary data when we have our estimate and the standard error. When heterogeneity is present, we can only use the inverse variance method. If heterogeneity is not present, we have an alternative to the fixed effects model with the inverse variance method, that is the Mantel-Haenszel approaches. And now I will discuss a little bit about the choice of the summary statistics in meta-analysis. So there is a paper by Deeks in 2002, and he discusses a little bit how do we should select the summary statistics for meta-analysis. And instead of the 3 effect sizes I've already discussed with, or I've already shown you, he has 4 effect sizes. Yeah, so he has the risk difference and the odds ratio, and of course the risk ratio. But he said we have to consider the risk ratio for a beneficial outcome and the risk ratio for a harmful outcome. Yeah, so we have to distinguish between 2 relative risks, whether we have a beneficial outcome or we have a harmful outcome. Yeah, and you will see in several minutes why this is important. Yeah, so when you select a summary statistic, of course, yeah, there are 2 things maybe you want to have. You want to have an interpretation of your results, maybe that you can tell also other people. Yeah, so interpreting the risk difference may be much easier than interpreting the odds ratio. On the other hand, maybe we have some mathematical properties of the estimator, and that's the other way around. The odds ratio is the effect size where the approximation to the normal distribution in fixed sample sizes is better, the best compared to the risk difference and the risk ratio. We have always discussed up to now that we want to have the homogeneity of the effect sizes. And there are some people, and I do like this idea, that we are not interested really maybe in the homogeneity of the effect sizes. We accept that there is some kind of variation. But when we have a control group, it could also be that it is a standard drug, and we understand the control group very well, we would expect that there is not so much variation in the control groups. And this is important also for the selection of a summary statistic. Yeah. So, and here is simply now an example where I want to show you what is the effect of coding of binary events, of binary data. So here we have several studies for thrombolytic therapy after acute myocardial infarction. We have the sample sizes in the treatment or an experimental group, and in the control group, and we have the events. Yeah. Okay. So, and of course, now we could use the events to do the meta-analysis. Yeah. But on the other hand, someone could say, I do not want to compare the events. I want to compare the no events. Yeah. And then the question simply will be now, what is the effect of coding for these binary data? So we do a random effects meta-analysis, and so the following is here for the effect sizes. Yeah, here we use the coding 1 for the events and 0 for the no events. And here we do it the other way around. Yeah, 1 for the non-events and 0 for the events. When we use the risk difference, the estimate when we use the coding 1 for events would be minus 0.0361. And we do the coding, non-events equal to 1, then simply the sign of the estimate changes. And the same is with the confidence intervals. We have here this confidence interval given when we have the events coded as 1, and the change is simply that you change the sign of the upper and lower bounds, and change the order. The p-values are identical in both situations. So for the question whether there is a difference or not, and using the risk difference, it does not matter how you do the coding. Events equal to 1, non-events equals to 0, or the other way around. It's more important for you than, or when you do the meta-analysis, for the interpretation, whether you want a minus or a plus. When you do it for the odds ratio, that's similar. For the odds ratio, then it is not that you have to change the sign. You have to look at 1 over the estimate here. So when you compute 1 over 1.76, you will end up with 1.31. So that's the connection between these two estimates. And you will do the same with the bounds of the confidence interval. Just take the inverse. And you will end up with this confidence interval. And again, the p-values do not change whether you use events equal to 1 or non-events equal to 1. So when these arc-seen difference, I have not used it a lot. It's also called Fisher's variance stabilizing transformation. There we have the same game. It's a difference. So the same game as for the risk difference. So that simply means that the sign will change. The signs also will change for the bounds, and the p-value will be identical. So what will happen now with the risk ratio? When we do the coding here for the events, we will get this result. So I want to show you here the forest plots. So, and we would get a relative risk of 0.8. with a confidence interval of 0.63 up to 1. And so now keep in mind that study number 5 has the largest weight, and maybe this study here 10 has the lowest weight. We have here the random weights. So, and what will be the effect when we now change the coding? Events equal to 1 to non-events equal to 1. You would see that there will be a change. So here now 4 studies are nearly identical with respect to their weights. Number 5 is no longer the study with the largest weight. Now it's number 6. So you have a change in the order of the weights here for the studies when you change the coding from events to non-events. And that is the reason why Deek said, you should say before you do the meta-analysis and you want to use the relative risk, whether you want to do the meta-analysis relative risk for a beneficial outcome or for a harmful outcome. That's the important thing you have to keep in mind when you do the meta-analysis for the relative risk, because the results or the weighting may change. So here in this forest plot, it's clear that 1 is in the confidence interval. We do not have a significant difference. Here it's not really obvious whether it's a rounding to 1, maybe it's 0.99999 or so, and we would have a significant result. So that means that the meta-analysis conclusion are not affected by the coding of binary data for the risk difference, the odds ratio, and these arc-seen difference or Fisher variance stabilizing transformation. For the risk ratio, we must consider whether the outcome is beneficial or harmful. That is important. And my recommendation is always when you do the meta-analysis for binary data with 2 groups, that you present an additional result, namely the meta-analysis just for the control group. I call it here simply a prevalence estimate. Simply see what is really the kind of risk you have in the control group. Because when you have some kind of differences and or odds ratios on the relative risk, so the interpretation always depends on the control group probability. For instance, look at a relative risk of 2, and you get a 2 when you have 0.4 divided by 0.2. You would also get relative risk of 2 when you have, let's say, 0.02 divided by 0.01. And the situations are completely different, whether now you have a, let's say, prevalence of in the control group of 20% or of 1%. So that's my kind of recommendation. Okay. So let me look. Maybe. So maybe we can first stop here and do a little bit of question and answer if there are some, because I still have few slides for the binary part, but we can discuss, I can show it to you, but maybe I think it's better now to discuss if there are some questions, now what I've presented on the binary data. Are there any questions or remarks?
Participants, please, if you have any question, you can either unmute yourself and ask the question, or you can also post messages on the chat group. Any question? Sir, I would like to ask one question. In the meantime, suppose while choosing the effect size, you said that obviously there is not a very black and white, rule. There is not a very black and white rule how to choose a effect size for a study. How to choose between different possible effect sizes. So one is one important thing which I understand is to see how interpretable the effect size is and whether it is according to the objective of the study.
Yeah.
And the second, do we also consider the fact that we should ensure more homogeneity among the effect sizes while choosing effect size?
Yeah, so everything is possible what you have mentioned. In, let's say, these Cochrane collaboration and the meta-analysis of clinical trials, often the odds ratio is used. It's because of some mathematical properties. But when you plan a clinical trial, I've never seen that the odds ratio would be the parameter of interest. There's always a difference of the probabilities, so the risk difference. And of course, that simply sometimes depends what the, let's say, the scientists, the doctors simply want to have, what they can interpret. Yeah, and most of the time they do not want to have an odds ratio, they want to have the risk difference. And yeah, so the homogeneity question, so in the now standard, let's say, biometrical or biomedical community, so it's a little bit, they do it a little bit on the easy way. They always say use the random effects model and do not really care about homogeneity. Yeah, but for me, it's a little bit important also that just looking also as the control group, whether there is some kind of homogeneity. Yeah, so I think when we started in 2000, it was around 2000 with this meta-analysis. So in the 1990s, I do not really remember the reference that it was not really the homogeneity of the effect sizes, but the homogeneity of the control groups. Yeah, and that was the one criterion at this point or at this time that you have to look, yeah, whether the control group is relatively homogeneous for do the meta-analysis. Yeah, because on the other hand, when we discuss the random effects model, also we had in the beginning also in Germany a discussion how much heterogeneity you can really allow for meta-analysis. Yeah, so and if this so tomorrow I will show you examples with a large heterogeneity where you then try to explain the heterogeneity. Yeah, so and these are still not really open questions. I think these are some kind of questions you cannot really definitely answer. Yeah, it depends maybe from the project to project what you want to do. Yeah, so it's really not easy to give a general recommendation what you really want to do.
Thank you, sir. Thank you so much. Any other question from the audience? If anybody wants to ask any question, you can unmute yourself and ask directly.
Yeah, so the participants, you have to ask, otherwise I'm so quick and fast. Yeah. So that's also a consequence of an online workshop. You also have, now we have had these online lectures here, and then you simply are much faster than as in presence, right?
Yes, definitely it happens in our classrooms also.
Yeah.
And also it it results in reduction in the kind of interaction we have in physical mode.
No. So maybe then if there are no questions anymore, I have still 5 or 6 slides for the binary part, and I just want to maybe give you an idea what is still additionally possible in this situation here
Sure.
for the binary data. Yeah, so maybe still 10 minutes or so, then I'm done for today. When we have the 2x2 tables, that simply means you can reconstruct in some sense the original data. Well, when you know that you have 10 successes and 12 failures in your group, yeah, you can say 10 times 1 and 12 times 0. And this situation, when we have 2x2 tables, is called individual participant data, IPD. And what we can do here is then a so-called one-step analysis that we apply generalized linear mixed effects models. That is what we can generally do for individual participant data, or when we have also continuous outcome, that we use linear mixed effects models. When we have no binary outcome, we can use generalized. Yeah? And one step simply means that we can directly use the data. And what I've presented up to now is more or less a two-step, so that in each study we compute an effect size and then do the combination. And there is a proposal by Steiner and co-authors for the application of sparse binary data. And here a little bit a slight different notation. And the important thing is when you have the number of successes in the experimental group, given the number of total successes. Yeah. So, and you calculate these conditional distribution. There's a close relationship to Fisher's exact test in 2x2 tables. Yeah, so the distribution is a non-central hypergeometric distribution with the odds ratio given in this form here. Yeah, when you do it in a 2x2 tables, Fisher's exact test, you have the central hypergeometric distribution. Yeah, because on the assumption that there are no differences, the odds ratio is equal to 1. Yeah, so here it's important now just that you know that there is a kind of distribution, non-central hypergeometric distribution, and the parameter is the odds ratio. Yeah, and then you can simply use likelihood methods. Yeah, you can simply look at the non-central hypergeometric distribution given from all the studies and do the meta-analysis. Yeah, or do estimation of the odds ratio. So the methods here are restricted to the odds ratio. Yeah, and you can do some exact likelihood methods also with random effects or for fixed effects, and this is kind of notation used in the R packages. Yeah, so it's not so easy to do the likelihood approach for this non-central hypergeometric distribution. Of course, you have to maximize something, and of course, your algorithm has to converge, and that's not always the case. And maybe you know when the probabilities are small, you can approximate the hypergeometric distribution by a binomial distribution. Yeah, and then there are also some alternatives that you are implemented here with this RL as a kind of approximative likelihood. Yeah. So, and these are, everything is implemented in the R package Meta 4 now with the function glmm. And I just want to show you some of the results just to give you an idea. Yeah. So the question simply first is one-step versus two-step approaches. So this is data set I guess I will start, no, not really tomorrow, my second lecture tomorrow, with this vaccination for the prevention of tuberculosis. And what you can do is first you can do this two-step approach. So I have used here the odds ratio, and you will get in the two-step approach. So what we have discussed nearly today, or all the times, standard and the HKSJ approach, yeah, where you get nearly the same results. Yeah, and when you use here the sum one-step approach, yeah, so you can use the exact likelihood and also the approximate likelihood. Yeah, for the exact likelihood in this example, you do not have any problems with convergence. Yeah, you simply see that you get also similar results, to the two-step approach. The one-step approaches are a little bit more computer intensive, and I haven't seen a simulation study up to now because of the kind of convergent problems to really see how good these confidence intervals and for the likelihood approach. Yeah, so these are always wild-type confidence intervals, and it's not really clear how good these confidence really are. Everything. Also, I've tried with a student a simulation study. Everything failed. Only for the approximate likelihood you get some results. Here is another example. Or otherwise, recall that there are not so many diseases with the vaccination, so that the probabilities are relatively small. Yeah, so that is the approximation to the binomial distribution you can use. So here is a larger data set, 22 trials, and I just want to show you here the results. The proportion of events are often larger than 50% in the trials. Yeah, so and the approximation by the binomial distribution is not good here, it fails. Yeah, so and that is simply what I want to show you here. Yeah, when you use the exact likelihood approach, you will get these results here. Yeah, and when you do the two-step approach, yeah, with the Polynomial estimator, you will get these results here. And again, the one-step approach and the two-step approach, the results are, yeah, relatively, let's say, close together. For the standard error, for the estimate, and for the heterogeneity parameter. Yeah, so and the result for the approximate likelihood here completely is wrong, you can say. Yeah, you cannot use it. Yeah, so you do not make any, let's say, syntax error in the programming. Of course, everything is running. Yeah, but the results here are not so good. Often, let's say, one uses these approximate likelihood because of the problems with exact likelihood for convergence. Yeah, but really recall that you only can use this approximate likelihood with the binomial distribution, yeah, when the proportions of events are close to 0 or close to 1, not in the middle of 50%. That does not work. Yeah, so and then the other problem, what we sometimes have, especially when, again, for the safety analysis, the 1, 0 and 00 studies. It could also be in the trials that we have, yeah, some zeros in some, yeah, here in this one is some single zero And then we have here 3 double zero studies. Yeah, so, and then you have, of course, for the exact likelihood, yeah, it's not possible because, yeah, you have too many zeros. Yeah, you cannot fit an exact likelihood here. And yeah, so that the maximum likelihood model is not appropriate. Yeah, but of course you can use the approximation for the approximate likelihood. Yeah, and here as an alternative, the Martin-Hensel method, and you can see that the approximate likelihood is quite close to the Martin-Hensel result here. Yeah, so, and these combination of the results here, that's also the reason why the Cochrane collaboration, especially in situation where there are some 1-0 or double zero studies, recommends the use of the Martin-Hensel approach. So this was everything I wanted to present today.
Okay. Thank you, sir. And again, if the participants, if you have any question, please feel free to ask. Yeah, I think the lectures were very clear and not much questions are there.
Okay.
So if there are no questions, I think so we can wrap up today's session.
Mm-hmm.
And we can meet tomorrow. It has been a long day for you. You must be very tired by now, I think.
Oh, no, it's okay.
So yeah, so Professor Gurpreet Grover is in a meeting. She wanted to join back, but she could not because she's a meeting late. So she'll be joining tomorrow.
Okay.
And by that time, let us say goodbye till tomorrow. We'll meet again.
Okay. Yeah, goodbye. See you tomorrow.
See you, sir. Thank you so much.
Bye-bye.
Bye.